Can you hear us?
Yes, yeah, now I can hear you.
We can hear you too, so it's all working.
Okay.
Can
you see the slides?
We cannot yet see this. Yes, we can see the slides, but they're not yet on the screen. So 1 second. Okay. We can see the slides, and you can see the room, right? Yeah. So we're all good.
Yeah, thanks a lot for that.
Okay, well, I mean, okay, it's time to start the session. Welcome to the workshop, and we have a very, an interesting program, and very full program, and Jacques would be chairing it, the first session.
Well, thank you. So the first session, we have 3 talks. So the first one is by Guillaume Much-Macagnoni about resource polymorphism, a proposal for integrating first-class resources into ML. This is a remote talk, but you can see Guillaume here on the laptop. Okay, you can start.
Thank you, Jacques. Hello, everyone, and good morning. I'm happy to see you because I have video feedback, so it's as if I was with you. This looks very nice. So the talk I want to present here is about something I've been working on and off for a while now, about how one could make ML a better systems programming language. So there was a proposal to add first-class resources into ML, heavily inspired by C++ and Rust. So first, a quick background on resource management in programming languages. So a resource, in the way I will understand it in this talk, are for instance, things with a cleanup operation, where you have to call for a file, for instance, some close operation to be able to release the resource at a certain point in the program. And well, the more you do systems programming or parallel programming and things like that, the more you're low level in your programming model, the more resources you have to deal with. And for instance, in multi-core OCaml, the notion of linear continuation or 5-bar is an example of a resource, because things go bad if you even forget to dispose of it explicitly. So we also see that in various frameworks that people are introducing in multi-core OCaml with custom schedulers, they introduce various notions of resources, various mechanisms to deal with the resources. So it's an important topic for multi-core OCaml. And this work in particular was started from discussions with industrial users of OCaml who said that they actually had issues programming with resources correctly in OCaml. So this example shows that it can still go wrong if you don't pay attention to exceptions that can arise. So in real-world OCaml, you would be advised to add a try with like this to close the file in case of error. So you always have to be mindful of the possibility of an exception. My definition of a resource would be a value which is hard to copy or dispose of. So you have to do something explicit if you want to copy it or dispose of it, if even you can. So in languages without a GC, this would be memory, of course. But even with a GC, if you have large amounts of memory, you might want to treat it as a resource. Those are the low-level abstractions from your OS, things that need to be cleened up, like mutexes. things for which aliasing is harmful. So when you want to control aliasing to, for instance, prevent data races. And in languages like Rust, we also see emerging abstractions appear. For instance, things for fault tolerance in Rust. And in programming languages in which you can program with resources, any data structure containing resources becomes a resource, etc. So memory management, usage of a value that respects a protocol. So if you want to ensure that the file is closed, that the network connection is open before communicating, etc. And so with all these constants, we see that correct resource management is an issue for correctness, efficiency, interoperability, and expressiveness. So just from this notion, I have a broad range of concerns to address. More abstractly, I want you to see resource management as techniques to reason about the state of the program. And how do we do this? How do we support this in the language is by supporting a notion of linear value. But be careful to state linearity as a safety property rather than as a liveness property. Something like, if I am at this point of the program, then I am sure that this or this function has executed. And I need to talk about modern C++, C++11, and Rust, which represent breakthrough for discussions and which are a direct source of inspiration for the proposal. It started with C++11, which introduces resources as first-class values. So it's a notion of resources assimilated to linear values that were a bit anticipated by Baker in the 1990s, but papers that were very rarely cited in the programming language community. And Rust is important because it extends the C++11 with better static type checking. And it showed that those concepts are also relevant for concurrent and parallel programming. The key concept of these languages is that of a destructor, which is a function that is called when a variable goes out of scope in a predictable manner, including when an exception is raised. In ML, you might have unwind product combinators, but the concept of destructor goes further than that. It is a type level abstraction. So you can have an algebra of types. You can have abstract types representing resources and so on that you can compose. And the big thing since C++11 is the notion of first-class resource, in the sense that with a runtime technique to manipulate resources, you can pass and return resources. You can put them in data types, in standard library containers, and so on. So you can actually program with resources as if they are first-class values. And it is a central concept because linearity and ownership in these languages are emergent phenomena of these types with destructors. For instance, in Rust, you've got borrowing, which follows from this concept, then uniqueness, so with linear borrows, the notion of external uniqueness via abstract data types, and so on. So I take it as a starting point to investigate such concepts in the context of ML. So the starting point for my investigation was work with Guillaume Combet back in 2017, where we actually reconstructed the notion of type with destructor in models of linear logic, essentially. And this gave us an understanding of destructors through some Curry-Howard correspondence. So destructors, types with destructors are understood as objects in a slice category. I won't enter the details, but the main result is that the structure that arises from that is very similar to the linear logic bang. However, instead of adding a kind of copyable types to linear types, like bang in linear logic, it removes copyability, so it adds a notion of ordered logic to intuitionistic logic. And this was a bit new kind of object that we didn't know until now in the context of linear logic. So the starting point is we want a type-based abstraction. We want to attach a destructor to a type to create a new type. This will give rise to ordered data type in the sense that if I destroy A after B, it's not the same as destroying B after A. And so ordered logic is weaker than linear or affine logic, but if we just look at what the type system does, I am still as expressive because I can destroy by calling the destructor, or I can move. It's ordered because move is an effect, and so A tensor B is not isomorphic to B tensor A. This explains actually phenomena that you see in Rust, this ordered phenomena. For models of linear logic and linear logic applied to programming language semantics, it solves an open question of how do we combine linearity and control effects, such as exceptions. So we answered the question, are types in Rust linear or affine? They are linear for values. Values are linear. The types are ordered. And if we just look at the static type system, the types are affine. So it's a pretty clear answer to this question. I had several goals and methods to come up with a proposal to extend first-class resources. First, I don't have a working prototype. In my proposal, I propose ways to translate some pseudocode into actual OCaml code. I did not address the question of a type system, which is left as a challenge. For this, there is a lot of relevant literature. And I talked a lot about language abstractions and how it could be implemented and how it works at runtime. So we want to find some ML-like sweet spot. And I wanted something which is rooted in programming practice and experience. So my goal was not at all to take the semantic objects and put them in a programming language. I was really inspired by how can I make ML a better systems programming language. And I was also inspired by not just the move semantics in C++11, but how it came to be, because by making resources first class, there were a point in language design where it would enable gradual migration from old code to new code. And they were careful of having something which could really interact with all the rest of the language. That was a key design goal, so that you don't end up with some kind of dialect when you program with resources that interacts poorly with the language. So I took inspiration from C++11 on this point. And there's no point in making a proposal that breaks backwards compatibility. I won't say more about it. basically, you want to add a new type. So you consider a type U, you add a destructor to it that gives you a new type T. And you want a type of borrows of these types. At runtime, you have a kind distinction. You need a distinction at runtime between types with destructors and types without destructors. So such a distinction of kinds is inspired by priority in linear logic. It's also very similar to the special traits of Rust, drop, copy. And so I will explain the new terms. For instance, if for a file, say from the standard library, I can create a new kind of resource that represents a file. And when I want to create a file, all this is looks really like ML. When I introduce the file keyword below, I am creating a file and I return a resource. And so the consumer of this resource, so the caller, will be responsible for calling the destructor, which these destructor calls will be introduced by the compiler automatically. For instance, if you have some value X in a function name drop that you do not use, then this will immediately call the destructor, but it's also the case with fancy drop. If you raise an exception, it has to be dropped. If you consume open a file by calling open file, so you receive a file in variable X, then you can move it elsewhere by calling another function. This moves the resource. If you try to copy it, you expect to receive an error, because if you copy an own file, you no longer know when to call the destructor. And you want it to interact with data types. So you want data types that contain resources. So if I have a list of file names, for instance, I want to be able to map this list to a list of a name and an open file. And the result will be a resource, which is a list containing resources. And what could happen? You could open a list of files. One of these files do not exist, so you get an exception. You expect that you have created a certain number of resources until now, until you get this error, and they will all be cleaned up automatically as soon as you get the error. So it would be a bit verbose to implement the same thing by hand. So I need a notion of polymorphism to be able to mix. So I want my resources to interact well with the rest of the language, and I want to avoid a language which is too verbose, where you have to duplicate code and specialize it to many different situations. And for instance, if you want to implement the map function on lists, you want to do it once for resources and non-resources. So you would write something like that. So you have to think about, how do I compile functions that are polymorphic. So I won't say too much about it, but it is possible, since there is a finite number of kinds to consider at runtime, to monomorphize. So there will be 2 options per distinct type variables to compile. So there is a lot more to say about it, but I won't talk too much about implementation strategies. I don't talk about the typing. The notations are inspired by the brilliant work of Jesse Toff and Ricardo Puccella about having a practical type system for affine types. Since I am ordered but still affine at the level of typing, this is a valid source of inspirations in terms of a type system. So I'd like to skip the notion of borrowing for lack of time. There is a notion of polymorphism of borrow, which is important. And I want to talk a bit about resource management, because one of my goals with this project is to mix different strategies for allocating memory. So in languages without a GC like C++ and Rust, they have different techniques to allocate memory. They use stack allocation and memcopy. So this is a different work than the present proposal. And they have unique pointers with ownership. They are tracking the ownership of memory cells so that they can free them promptly and not sooner than needed. And this is supposed to be as efficient as malloc and free. And they need to use various strategies like having reference counted pointers when they want to share data and so on. And reference counted pointers have many drawbacks. Most of you know about it. So one of the most important for ML is the lack of cycles, for instance. And so there are ways to improve reference counting by various methods, and you will have a talk later on that. And I wanted to talk about this paper, which highlighted that the difference between reference counting and garbage collection is a bit misleading, because we have actually a variety of techniques that are a bit in between RC and garbage collection. Reference counting, so we want to get rid of it. We prefer GC because it handles leaks. It can be nicer for latency and so on. But still, reference counting is good for timely resource destruction. So I understand languages that use reference counting for that. So the correct point of view to me is to see two possible directions. If you start from RC, either you improve it in certain ways and you get to some kind of GC. You can improve it in a different direction by preserving different qualities of reference counting, by pushing it towards ownership and destructors or an RRAA. So in this diagram, OCaml will be far to the right. And later you have a talk on Perseus, and I put it just a bit to the right. So Perseus, they experiment with reference counting where they can reuse memory. So it's nice for experimenting about functional programming where you can reuse memory cells. And I put it a bit to the right because it is still not possible to reason about when your memory is collected, in the sense that if you had resources attached to values, say finalizers, like for GCs, you would not be able to predict when they run unless you know the algorithm. And my goal is to preserve this property, to be able to predict when the resource is collected, because I want to be able to handle other kinds of resources, and I want, if I have large amounts of memory, I want to be sure that it's not collected in the middle during a hot loop, for instance. And so I want a language where I have both RAA and GC. So there are advantages to GC. And on the other side, with RII, we get a lot of different advantages. So I won't enter the details to have some time for questions. But mainly we avoid the drawbacks of reference counting by a static ownership discipline, which removes many issues such as cycles. So I have two works, two experiments presented at ML and OCaml workshops on this. So one observation is that one drawback of RII is that you need to have an ownership and borrowing discipline, and you need to traverse the whole structure on destruction. So you cannot benefit from a general hypothesis. So the claim is that since you are already paying the cost of that, then you most likely want to allocate all your resources, everybody of kind O that I showed in the previous section, you want to allocate them linearly so that you can take advantage of linear allocation with reuse. So there are two experiments. One is box root, work with Gabriel Scherer. When I explain how I can embed a garbage collected value into an own value. So it's the idea that you are going, if you create a root for a GC, you are creating a resource because you will need to unregister the resource. And so it's a bit like the smart pointers in Rust, where you make a resource out of some memory, and in this way you embed the garbage collected world into the resource world. The result of the experiment is that it can be done efficiently. It's interesting because you are mixing techniques from efficient allocators and techniques from efficient GCs when you implement that. And one of the conclusions is that the cost of introducing a root in this way is already paid for in a certain sense. It's not more costly than into allocating a memory cell with malloc. And in the other direction, we can embed the own world into the garbage collected world. So it's the converse direction. If I borrow something which is owned, I can pretend that it's allocated as a normal value because I have a uniform representation of values. And when I call a function meant to manipulate garbage collected values, it actually does not care how it has been allocated. So for this, there is an experiment at OCaml 2022 where I showed that it does not cost anything to add a way to discriminate between people inside and outside the heap, inside the marking loop of OCaml. Actually, it made it run a bit faster, but negligibly so. And that was a bit of a surprising result. And with these two features, one can mix GC allocation and linear allocation with reuse. So there are challenges for typing. I won't enter the details. And here is a summary of the talk. And I will welcome your questions.
Okay, so are there questions? Yep.
Hi, Guillaume. This is me, Neil Krishnaswamy.
Hi, Neil.
So in C++, you don't just have move and drop constructors, you also have copy constructors. And I wondered if you know, like being able to implement your own contraction was something that you had considered or which you thought might be either useful or harmful.
Let's say definitely harmful because there is too much freedom in C++ in this respect, in my opinion. I'm not sure that we want something which is automatic, like a copy trait. And then if you wanted something like reference counted, this is perfectly valid, some kind of reference counted resource, but you would not want to make it a core trait of the language. As in, actually, I'm not saying anything new. This is what they do in Rust. Like the clone of RC is not at all implicit. So it's orthogonal to what I'm proposing.
Ron Minsky from Jane Street. I'm curious how you think this work relates to the work on mode and uniqueness modes and stuff that's currently happening at Jane Street, and whether that kind of fits into the kind of typing story that you might fit into, that you might want to have for this kind of resource management.
Oh, there is a lot to say about it. So I have to thank a lot Leo and Steven, because we had a lot of discussions about this proposal, and they've been doing like something like unboxing, which is orthogonal, but which I mentioned was still useful so that this proposal pays off dividends. And the work on ownership has a different method, and one aspect of my proposal was that, or at least I was hoping that by having something ambitious but with a large payoff, we would motivate working on a much more expressive notion of ownership and borrowing. Whereas what I have seen, so I have only seen the blog post on the locality thing and ownership and all that. But there are more like low-hanging fruits to reason about ownership. So it's a bit orthogonal in a sense, but I'm hoping that with our resource management proposal, we would be able to motivate and push it further towards something more expressive. Thank you.
So the next talk is about modernizing standard ML of New Jersey, a status report, and John Repe is going to give the talk. With the okay.
Test.
Should be on. Okay, does that work? Okay, so this talk is basically going to be sort of about what Dave and I have been doing for the last, 5 or 6 years, and hope to continue doing for the next N years. So and it's, you know, it's in part sort of a we're not dead yet kind of talk. You know, feeling better all the time. So, all right. So, just to give you some background, because I suspect Standard ML of New Jersey is actually older than some of the people in the audience. This is a system that dates back to the March 86. Okay, so dates back to the over 35 years ago, and it is was originally, you know, designed around the traditional functional REPL type model of interaction, and a lot of people's introduction to it is through the REPL, but it's not an interpreter. We frequently get, you know, email messages about the interpreter, but there's no interpreter. It's actually from the very beginning, it was native code generation on the fly, and also then a batch compiler that produces files with the native code in it. And one of the early original design philosophies, I don't know if this was ever stated explicitly, but it can sort of be reverse engineered from the implementation, was that the system should be self-contained and self-supporting. So minimal dependencies on the outside world. So in particular, the only external dependencies were really, you had to have a C compiler, you have to have a shell, Unix or DOS, and you have to have make, or on Windows, nmake. And if you had those things, you could basically build the system and run it. So this philosophy meant that, of course, things like Yak, Lex, build tools, all of that stuff had to be written for the system. And so there's a lot of that, tools and libraries, and they're all, largely that code is all written in standard ML. And that was, you know, in some respects, that was a sort of a good demonstration that you could build these, you know, of reasonably large and robust production functional language implementation, and it would actually work. But the downside of this approach is that it's a lot of extra maintenance, right? There's a lot of components, and a lot of those components were written by people who are no longer actively involved in the project. So, you know, Dave and I basically have to sort of figure out how do these things work and how to fix them. And by and large, they're pretty solid and robust. They don't, you know, they don't break, but occasionally people discover corner cases or problems, or we break them by accident. And the other thing is the system has, as many systems do, has played a kind of dual role. It's, on one hand, it's been used in production, it's been used in commercial products, it's been used heavily for teaching, still to this day, but it also was a vehicle for research, right? So Andrew Appel and his students did lots of stuff. Zhang Xiao subsequently at Yale and his students did lots of stuff. There were people at University of Chicago who've worked on it as part of their thesis research. And so, you know, systems like that accumulate various kinds of barnacles, right? The, you know, bits of code that was there to support someone's experiment or someone's PhD, but aren't really, they're not supported, they may not work anymore, but they're sitting there occupying space and intellectual effort. So these are all sorts of issues that we've had to deal with. So what are we trying to do? Well, first of all, we're trying to streamline and document the existing code, and in part this will hopefully you know, allow the system to continue on maybe, you know, 50 or 60 more years after Dave and I are in the ground, so to speak. It will, we've been removing unused, these barnacles, this code that's bit rotted away, doesn't really work, doesn't do anything useful. We've been doing wholesale rewrites of components. Now this is actually a tradition in the system. I think there isn't anything in the system that really dates back to 1986. You know, large parts of the system have been rewritten. Some of them rewritten multiple times. And we're we're also trying, as a process of this rewriting and restructuring, we're trying to make the compiler more modular, right? So currently it's very monolithic in its design, but really, a modern compiler ought to be structured as modules, not as some big monolith. And once you have it structured as modules, you can then start to use those modules for other activities, like building, say, an LSP server. And then also, once we've got this cleaner base, we can start to add new features and components that weren't really plausible to add in the past. So this is the basic agenda of what we've been doing and what we're hoping to continue doing in the future. So I want to give a bit of an overview of how the system is organized, just because otherwise the rest of the talk won't make a lot of sense. So at its heart, there really are three main components. First of all, there's the standard ML compiler and supporting libraries. So this is like the basis library, SML New Jersey library. That's about 225,000 lines of code, not counting comments and white space, et cetera. So just code. And this supports both the interactive and batch compilation, as well as library support for applications. Then there's the compilation manager, which is fairly tightly integrated into the compiler, but is conceptually a separate piece of code. That's about 10,000 lines. That was developed by Matthias Bluma. And then there's the runtime system, which is about 25,000 lines of C code, and maybe another 1,500 lines of assembly code and the assembly code really supports 4 different architecture, operating system combinations currently. So that 1,500 lines is not for one machine, but for 4 machines, if you will. Now, at runtime, so when you one of the things, because it's self-supporting, we don't depend on object file formats. So when we compile a module, what you get is, well, I should say when you instantiate a module, what you get is a tuple, which represents the dynamic components of the module, right? The values, the exception definitions, but not the types. And so that means that structures just become functions that take the free components that they depend on and produce a record, and functors are functions that take the free components and then return a function that takes the arguments to the functor, and then that in turn returns the record. So everything is, at this point, everything is just lambda calculus. And since everything is lambda calculus, linking is beta reduction. And so that's very nice. It's completely portable, and we don't have to know anything about operating, object files or anything like that. So standalone executables, to the extent that they exist, are actually built by batch compiling source code into binary files. We have our own sort of minimal representation of binary files. There's no symbol information in these things. This is really just code, and like how much code is in there. There's a little bit of extra information that the bootstrapper needs, but I won't go into that. So you compile to machine code files. We call them bin files. You then load those in. You run the runtime system in Bootstrap by doing all these beta reductions. And at the end, you have a SML function that you can run, and that SML function typically exports a heap image, right? So it's just a snapshot of the current heap. Write that out as a file, and then that's your executable. So to run the executable, you can technically link it with the runtime system, but typically this is done by just dynamically loading. So it's like jar files in Java, right? You just read in the heap image from the file system, and away you go. And even when I say you statically link, what I really mean is you just embed a copy of the heap image into an executable, and the executable then just reads, rather than reading from the file system, it just reads from its own executable. Okay, so I also want to talk a little bit about the details of the compiler. So it's very conventional, source this, quote-unquote source-to-source transformations between intermediate representations. So you start with a parser, you get something that we call AST that gets elaborated into absin. Absin is then translated into Flint, which was this intermediate representation developed by Zhang Shao and his students. It's a strongly typed intermediate representation based on F omega. It's actually a very impressive piece of engineering because it scales really well, which is typically not true, or I should say, which is a challenge for very rich intermediate representations that have lots of fancy type features. I won't cast aspersions on other systems. And it models both core language and module level types. Pattern match compilation is embedded as part of this absent to Flint translation. So Flint is used for various high-level optimizations. I think originally the intention was, in fact, to do all optimization at the level of Flint, but that never really fully got fleshed out. I think Stefan Monnier did inlining, but there wasn't a lot. There wasn't the full complement of optimizations. But there are a couple that are really actually important to performance. One of them is a type-based arity raising scheme. This is a little bit like Xavier Loise's idea for using types to do unboxing. There's some space safety issues there you have to worry about. And there's the choice of representations for things like data types and function arguments are also done at that point. That's then turned into CPS, which is continuation passing style. And we throw away most of the type information. We do CPS to CPS transformations, which are our basic low-level optimizations, such as contraction or shrinking, inlining, uncurring. Then we rewrite the CPS into closure passing style, which is also CPS. Nice pun there in terms of the acronyms. And in fact, is also the same intermediate representation, except that the invariants are somewhat different. So there are no higher order functions at that point. And finally, you take this first order closure passing style representation and you turn it into machine code through the ML-RISC framework. And so that's that's how the compiler works. Okay, so I've used up 12 minutes and I'm now ready to actually talk about what we're doing. Okay, so in the 2010s, there were a few things that happened. So the first one was we realized that 32-bit systems were not long for the world. And in particular, Dave and I both like to use Macs, and Apple has said, well, at some point in the late 2010s, you're not going to be able to use your 32-bit Mac anymore on the latest operating system. And this also, Linux is basically had dropped mainline support for 32 bits. In addition, the Milton folks were experimenting with successor ML features in their compiler, and we sort of wanted to maintain compatibility with that. Successor ML actually has an implementation that Andreas there did, and on top of Hamlet. So it's not completely a paper design, but it's basically a collection of ideas about how to improve and refine the definition of standard ML. And there is, in fact, a version of the definition of standard ML that has successor ML edits to it that exists. In addition, sort of in parallel to that, we're enhancing the SML basis library so these things were all things that basically motivated us to get started actually working on the system in a serious way again. And so in 2016, so we were at around version 110.80 at that time, we started the process of trying to port to 64 bits. This actually turned out to be a lot more work, I think, than we had anticipated. And in particular, it was a lot of work because we had many, many years worth of code that had been written assuming that computers were 32-bit machines. Even code written after the alpha existed. And after MIPS was shipping 64-bit processors, people were still saying, oh, computers are 32-bit machines. And those assumptions just completely permeated the intermediate representations and algorithms for various places and stuff. And it was just, it took a long time to sort of root them all out. Once we had sort of generalized in that respect, the actual process of porting 64 bits wasn't so hard. We already had an existing AMD 64 code generator that Mike Rainey, Mike's back there, had written as part of the Manticore project. His compiler, this was part of MLRISC, generated assembly code, but someone else had come along and added machine code, and I'm sorry, I don't remember who it was, but I should give them credit for that, and I just basically had to debug what they had done and get the assembler and stuff working. So it by December of not 1996, but December of 2019, we basically had a stable 64-bit implementation, and that's really been the default since then. Another thing we worked on about the same time is this, what we call deflintification. So Flint had sort of extended its tentacles throughout the compiler, and we sort of had to chop those back, and that is mostly done now. I think there's one example in the front end that still needs to be removed. Dave rewrote the handling of overloading for operators and literals. This is a kind of ad hoc overloading. We've been, of course, tracking the changes that Milton was making to successor ML. Most of these are basically syntax. They're not really that deep. The one more significant non-syntax thing had to do with OR patterns, but we actually already had support for OR patterns, so we were good. And we also updated the runtime system code to C99 because it basically was ANSI C at that. Yeah.
One more thing is the rewrite of the match compiler, which we talked about last year.
Yes, I will get to that. I anticipated that. That happened later. Okay, so in 2020, we decided to replace the MLRISC code generator with one based on LLVM. At the same time, we were running out of version numbers. And this is actually the second time we've run out of version numbers. If you go back long enough in history, there actually was a 0 dot in front of 110. So we got up to like 0.100 and kept going. And eventually when we got up to, I think, 110, and we started iterating like 110.1, 110.2, et cetera, we said, okay, let's drop the 0 dot. So, so that happened back when we were all still at Bell Labs. So we were running out of version numbers, and so we made the decision, which I think is a good decision, which is we split the system into a legacy branch, and those numbers are like 110.99.4 is the latest version there, and a development version. We're currently at 2023.1, where we've switched numbering conventions. We're using year dot release number for that. And the idea here being that people can still use the legacy branch. It still supports 32-bit executables, and we can do whatever we want in the development branch without hurting people. So the development branch does self-compile if you have the right machine, but it's not really ready for production work. So it gives us this kind of a sandbox where we can break things without affecting end users. It is currently the focus of our ongoing and modernization efforts. So, in fact, what have we done so far? Well, we re-implemented the pattern match compiler, and as Dave mentioned, that was talked about last year at the ML workshop. There's this LLVM code generator, and I'll talk a little bit more about that in a moment. That was also described in an IFL 2020 paper. There's a new pretty printing engine, which Dave is going to talk about in the next session. We are working on rewrite of the runtime system with major GC improvements. I'll talk a little bit about that in more detail. And we also migrated to GitHub last year. And that actually turned out to be a lot harder than it should have been, but mostly because of the bug database and turning those into GitHub issues. But it's done. Okay, so I'm going to talk about the code generator. So we use MLRisk. MLRisk goes back a long way. We had a paper, Law George and I had a paper in 1994 at the compiler conference about it. Later papers in PLDI about it. And it's effectively allowed us to support native code generation, good quality native code generation for a lot of different architectures for many years. I mean, in the history of standard ML, we've supported 10 different architectures using that framework. We currently don't support all of those. Many of them don't exist anymore, but you know, like VAX, for example. It's a very nice design from many respects. It's a mechanism, not policy design, and that's really great if you're trying to do non-standard runtime system models, because it doesn't bake in a lot of assumptions about, oh, you have a stack, oh, you have this calling convention, et cetera. It's all, you roll your own. But it's not actively maintained. I mean, Mike really is the last person to do a substantial addition to it, and that happened in the, I don't know, around 2008 maybe. So, it has some bugs, and so we wanted an alternative, preferably one that someone else was maintaining. And the obvious choice, of course, in the modern space is LLVM. That is the, you know, sort of the big, mature, widely supported system. So we had some goals and some challenges. So we wanted to preserve our existing runtime model, and our runtime model is based on this idea of heap allocated return continuations. So there's no stack. All things get passed in registers. We wanted to maintain the interactivity of the existing code generator. So you would type stuff at the terminal and it would come back immediately, and you wouldn't have to wait a long time. We needed to be able to generate raw machine code in a format that is compatible with our runtime system. We wanted to keep the C++ code as sort of simple as possible. So we didn't want to be writing a lot of C++ compiler code. We wanted to be writing SML code that compiled stuff. And lastly, I mean, for people familiar with C++, or sorry, with LLVM, all of these things are actually hard to do in LLVM. I don't really have time to explain why, but you can ask me after. But LLVM has a really heavy bias towards C and C++-like languages. It is designed to support compilers that use that runtime model. And that makes it a challenge for people who are doing something very different. So how did we do this? Well, we used this thing called jump with arguments, which we developed, one of my students and I developed for Manticore, which was this parallel ML compiler we were working on in the 10 years or so ago. And we added an extra low-level IR to that's more explicit than the first-order CPS that we had. And we use ASDL, which was a tool that was developed many years ago to allow compiler components to talk to each other. There are, you know, compiler components written in different languages to talk to each other. So we serialize the intermediate representation, pass it into the runtime system, and the runtime system uses that, deserializes it, and uses it for code generation. So we have a code generator now that sits on top of this LLVM C++ API. Currently, we have backends that support x86, 64, and ARM 64, but there's some serious bugs. So it works in some limited situations. It works well enough to self-support, but it's not really ready for prime time yet. And again, there are details in this IFL paper. just quick performance numbers because I know I'm starting to run out of time. So it slows the compiler down sometimes by a lot. I think the worst, well, these are really small examples, but like if you compile the compiler, it takes 3 times longer using the LLVM backend than the straight backend. But it's not too, it's only a little bit over 2 minutes, so it's not so bad that it's going to really be terrible. And we have very good incremental recompilation support. So as long as you don't need to compile the whole compiler, it's not so bad. On the other hand, things actually get faster. Typically, I think sort of roughly 15 to 20% is probably a good guess for performance improvement. So we are picking up some benefits from that. And of course, we get the portability benefit, which is perhaps the most important thing. Okay. So I have 5 minutes, I think. My clock says 5 minutes, so. All right. So another major thing that's sort of currently work in progress is a rewrite of the runtime system. And LLVM, the code, and we stripped out a lot of code from this source tree, but we still have 1.6 million lines of C++ code attached to our small 25,000 line runtime system, right? So the C++ code just completely dominates. Now, it's also the case that modern versions of C, and by modern I mean versions that are 20 years old, are not actually supported on Windows. Windows kind of stopped with ANSI C, basically. Some features are, but not the full language. And it was also the case that we actually had sitting around a version of the runtime system that was written in C++ in the mid-2000s. And so for these reasons, decided to basically sit down and rewrite the system, but using modern C++. So in the C++ community, anything after C++ 11 is called modern. And specifically, we're using C++ 17 because that's the current standard that LLVM is using. So why do we want to do this? Well, one thing is we can actually take make fairly good take advantage of templates. That reduces the code size. So the C++ code is actually about 10% smaller in terms of source lines than the C code. We also can make some parts of the system more type safe, in particular the interaction between the runtime system and SML. So let me just briefly talk about that. So we introduced C++ classes that represent SML types. So for example, string value is a SML string, and we can use templates like list type here as essentially the list type constructor from SML, but as a C++ template. So you can have like a list of strings. And so here's an example. This is from the old runtime system. And in the old runtime system, we basically use these macros here to sort of convert between between the SML representations and C representations. And hidden in this is actually a conversion back the other way, along with some error checking. So when we write that in C++, we now just basically write down a type. So here we're saying this thing is a triple. It's the first thing is a value, because we put all the integer types just become values. We don't have specific classes for those. And it's a vector of bytes and another integer. And we then can just use our just extract those values directly in a somewhat more type-checked way. And the nice thing here, though we don't currently exploit it, is, two nice things. One is this code can actually do runtime checks to make sure that the argument is actually plausibly a triple, and of the appropriate types. And the other thing is this thing and this comment are actually not reflect the same information, and so there's actually potentially an opportunity there to be machine checking the interfaces. Okay, so I'm almost out of time, so I'm going to skip talking about garbage collection. So I'll just skip the garbage collection because that was. I'll just talk about future plans, and that's the last slide. So, okay. So what do we want to do in the future? Well, first, we'd like to sort of continue to use ASDL. There's a pickler in the system that's a handwritten thing that's a very difficult thing to update. So we would like to replace that. We have plans for rewriting type checker and module system with better error reporting. This is also part of the sort of making the compiler more modular. So we'd like to take these, we'd like to have the compiler be a bunch of libraries, and then we can have the REPL be a program, we can have the batch compiler be a program. Someone can put together an LSP server as a different program, but these things will be built on a set of common libraries. And so I think that will be a much better architecture. A lot of these things are just rewriting things that need to be rewritten, so rewriting the compilation manager, and we'd like to extend the compilation manager with MLB support, which is the system that the SML kit compiler uses and the Milton compiler uses. We would like to continue adding successor ML features. We did a paper in 2019 at the ML workshop about how to do the guard pattern, or pattern guards, I guess they're called. I've got a student who's working on rewriting the safer space closure conversion algorithm, but to use actual higher order control flow analysis information rather than the very limited information we currently use. We wanted to replace our current very hacked up installation system with something maybe based on CMake. And I was inspired by Andreas's keynote to realize that, in fact, particularly if we modularize the compiler, it should be fairly easy to build a WASM backend, because once you get down to the first order representation we currently are using, I think the gap from that to WASM is actually going to be very small. So that is my talk, and I apologize for running over time.
So when you go through all the effort of rewriting the runtime system, like the height of current days is using Rust, right? Was that a consideration at all?
So I guess I thought about it, and I would say there are two reasons why I didn't do that. One is a large motivation to do this is basically build compatibility with LLVM, because LLVM is clearly going to be, is going to be the dominant piece of source code in the runtime system. And so using the same language as LLVM is written and is nice. We won't have to, there won't have to be any kind of shim. I assume there probably is a Rust wrapper for LLVM, but then you're dependent on a wrapper which is dependent, so when LLVM changes, now we have to wait for the Rust people to update their wrapper, and then we can update our code, so I think it introduces a lot, sort of more moving targets, I guess is one way to say it. And I don't know, I know Rust in a sort of scholarly academic, I've seen a lot of talks on that way, but I haven't really written any serious code in it, so. Where is it? Thank you.
About semi-explicit polymorphic parameters.
You will part one this.
All right. Right. Okay. So, I'm Leo from Jane Street. No, just here. And I've broken the thing. Okay, that's still working? Yeah, all right. Right, hi, I'm Leo from Jane Street. I'm going to tell you about some work I did one afternoon to add semi-explicit, to add support for polymorphic parameters to a camel. So what are polymorphic parameters? Right, so here is a function that you might write called foo, and it's a higher order function, and it takes in a function called transform, and it's going to run that first on a list of integers and then on a list of strings. And you might call such a function by passing it a polymorphic function like list.reverse. And obviously the problem with this is that if you try and do it, you just get an error complaining that that on the second call to transform is expecting a list of integers, and it got a list of strings. And that's because in classic Hindley-Milner, your type inference, your parameters can't be polymorphic functions. They have to be monomorphic. Now, in a camel, there are ways to work around this already. So you can, record fields can be polymorphic. So you can kind of define a record with a polymorphic function as its field, and then use that to implement foo. But now you've got to kind of wrap, your call site's going to have this like wrapped record on it, which isn't great. You can do it without even having to have a type definition by using object methods. Sorry. So so up here I kind of you have foo, and you have a type annotation saying that it takes an object with a polymorphic method, and then you can call it. So you can use the function polymorphically, and then you can call it with this thing. Now, obviously, this isn't great either because firstly, this is very heavyweight, but in particular, this type annotation here is required. And so the way that this works is described in semi-implicit first-class polymorphism for ML by Jacques Guéric and Didier Remy. That system is often called polymL, although it doesn't actually call it that in that paper. And the core idea of that paper and the way that it's used to implement this is actually we're just going to be reusing that mostly. And so I'm mostly going to be talking about kind of reminding people how that works. But yeah, what we want to do is just to support this code. We just want to write a type annotation on transform, but nothing on the call site. Just be able to just call it directly. Right. Well, yeah. As I said, just going to kind of reuse the underlying idea from polymL. So, kind of a summary of the talk. So, again, I'm going to talk a bit about the polymorphic parameters. I'm going to focus in on what I'm calling labeled types, the core technique that was used in polymL and that we're reusing here. Talk a bit about the implementation and a little bit about some related work. Right, so what we're trying to do is to support polymorphic types in parameters. So the change that we're making in terms of the type grammar is so here's the kind of classic Hindley-Milner type grammar. You've got types and you've got schemes, and only the schemes can be polymorphic, and the schemes don't appear inside of the types. And we want to just change it to this. We just want to adjust one of those taus to a sigma, so that we can have some polymorphism inside of the function arrows. It's worth noting that the equality on the schemes is going to remain the kind of ML one, so quantifier order doesn't matter, and if you have a useless quantifier, it's as if it wasn't there. Yeah. Right, and so we want to if we want to make this change to the type grammar, we basically have to do two things. We're going to have to change the an introduction rule to kind of how to create functions with polymorphic parameters, and an elimination rule for how to call them. So here is the traditional rule for lambda in Hindley-Milner system, and obviously it's restricted to just having a type, not a scheme, on the argument. So it's it's a type. And so if you do the naive thing and just kind of say, let's make it a scheme, that seems easy. Unfortunately, that doesn't work because the type inference for such a thing is undecidable. I don't want to try and describe it in too precise detail why that's undecidable. I can kind of give you a basic idea of it. So let's say you're trying to work out, you've got like, for all alpha, something list to something list, and you're trying to use it as an int list to int list. And fundamentally, you kind of have two options here. You can either kind of fill in that weird x with an alpha and kind of use the polymorphism and then instantiate it down to int list, or you could just say that x was int from the beginning. And unfortunately, this kind of dilemma is equivalent to what's called semi-unification, which is undecidable. So here's kind of the traditional look of semi-unification. So you've got like sigma and tau. The sigmas and taus are all kind of types, like first-order terms, and you've got these. You've got this substitution S, which is kind of being applied everywhere, and that's like unification. And you've got these two different substitutions being applied just on the left-hand side, I1 and I2, and that's like kind of instantiation. And you just, the difficulty is that you can't really decide whether you should use the S or the I to solve the problem, and that decision can be undecidable in the general case. So what we're going to do is we're just going to demand that the parameter be annotated, that if you want to introduce a function with a polymorphic parameter, you just have to provide a type annotation right there on the lambda. So that one's pretty easy. The difficult bit is elimination, because we're like, the whole point is really to do the elimination form without any additional annotation, to have the same elimination form for functions without a polymorphic parameter as functions with a polymorphic parameter. And there, you kind of the main problem you kind of run into is a lack of principal types. So here's another example, also called foo. So it's a higher order function, takes an f and a g, and the key thing here is we pass the identity function to f, and then we pass f to g. And the issue here is that there are two types you could give this, and they are not. One is not an instance of the other. So either you can say that f demands that it be given a polymorphic function, and then g has to provide it with a polymorphic function if it wants to use f, or you can say that f doesn't actually need any polymorphism, and then g doesn't need to provide a fully polymorphic function. So in one you can strengthen f and weaken g, or you can strengthen g and weaken f, and so that's why they're kind of incomparable. Maybe make it a little clearer with like some examples. So here I could pass foo a polymorphic function that uses the polymorphism of this ID, both int and string, and then g has to pass f. On this line down here, g has to pass f another polymorphic function, so it has to use ID. And so that works with the first type, but not the second. Or we could have this kind of call site where foo doesn't use u polymorphically, just uses it at int, and then g is able to take advantage of that and just provide a function that only works at int. And so that works with the second type, but not the first.
Yeah, can I ask a quick clarifying question?
Sure, yep.
Do I need a microphone for the...
Is there one? Yeah, there's one there.
Right. Oh, thanks. Just to say, in a lambda without annotation, which is what this original function definition was.
Yep.
There's then the bound variable is going to get a tau type. Right?
Yes.
Okay.
Yes.
But that tau type can have sigmas on the left of its arrows.
Yes. This is not a predicative.
Kind of emphasize that.
Yes.
But in just naked, unannotated lambdas, you're going to try to infer tau types with sigmas to the left of arrows. That's your goal.
Yes.
Okay.
We're stretching infer there, but yes. Yeah. This is it's in predicative, not predicative. It really does let you have. Yeah. Exactly. That's not too bad. It did literally take an afternoon. So. Right. So the aim here is we're going to not infer it. We're going to you want to assume f is not higher rank. So given no other indication, f doesn't require polymorphism unless it is annotated. And so here's an annotation, which sounds like it's running counter to what I just said to Simon, but it's not quite. Right. So unless there is some kind of annotation somewhere where you know that the type requires the polymorphism. Of course, the problem is it's not enough to have information just be coming from some annotation. So here is an example. So here's the foo example, but I've inserted an if. So the kind of the old body of foo is in the else clause, and then in the if clause we kind of have an annotation telling us that f requires polymorphism. And so you might imagine that this might work. You go down the if branch and you see that f requires polymorphism, and then you get down the other side and you go, well, I must be polymorphic. But then this is clearly order dependent, right? Like if I just flip the clauses round, it'll stop working because it won't have got to the bit where it learns about the f. Or if the type checker changes its mind about the order it wants to do things, it'll stop working. You really don't want to have this thing type check either. So kind of the question essentially becomes, when is it principal to kind of inspect some type information? When can you do this in a way that's not going to cause this kind of order dependence? And so, right, so what we're going to do is we're going to look at this example in a little more detail and kind of see where the problem is coming from. And so if we kind of, again, classic kind of algorithm J, Hindley-Milner, try and type check this top one, and we go down the then branch first, we will see, when we get to the point here, where we're trying to type the call to f, we will have in our context that f is in fact a polymorphic type, and we can kind of, we have that information. But if we'd gone down the else one first, we would have alpha, and we wouldn't have had the information. And so what's happening here is Gamma is kind of acting like a side channel. It's like smuggling some information in that you wouldn't necessarily know yet, depending on the order you've done things. And so what we really want to do is we want to know if we could tell that this function in the context and this function here were actually the same, that they'd come from the same unification variable. That's how the information had gotten to us. We know it isn't really safe to look at that information because we don't know that we would definitely have it at this point. And so what we really need is if we have some notion of identity on the type, if we know that this alpha to unit is the same as this one and not some unrelated other one that just happens to have the same form, then we can kind of solve this problem. And so what you're going to do is just kind of, so what we're going to do is we're going to put some labels on the types, on the arrows in this case. And so if you have a label on the arrow, you can kind of say, this label is the same as this label. It's not really, this one is shared with the context. And so because there's this sharing between this type and the context, it's not really going to be principal to like take advantage of that information. And so, right, and this is very similar to, I think it's very similar to the gen rule side condition. So in kind of Hindley-Milner, you have the gen rule has this side condition that says, like, if alpha is not a free variable of gamma, then it's safe to kind of generalize it, and in particular, it's safe to later on instantiate it and kind of do something. And one way of thinking about that condition is to think of it as saying, well, if we know that it's really, really a variable, then we can generalize it and copy it and instantiate it. We have to know that it's not secretly int, that we're not going to have, there's not some requirement in gamma that later on says, it wasn't alpha, this was just a unification variable that you didn't know that it was int yet. So it's kind of, you can think of it as a way of saying, like, are we done inferring this thing? Like, do we know everything about alpha? Like, if alpha appears in T, doesn't appear in gamma anywhere, kind of all the constraints in alpha are known, and so it's safe to, treat that information as kind of principally known. So what we do is we can do the same thing with these labels. We can kind of extend our schemes with a notion of with a for all on labels that indicates that the label in question, which is used in the kind of squiggly sigma, is not present in the context anywhere. And we can add instantiation and generalization rules for these labels. And then we can finally write our elimination rule for the polymorphic parameter, for a function with polymorphic parameters. And the key thing here is this for all. This says if you've got a function that takes, in order to apply a function that has a sigma on the left, you need to have the label on that arrow needs to be generalized. It needs to not be shared with its context at all. Yes. Right, and so I thought there was another slide between there. Okay, fine. Right. So the other aspect of this is what happens with an annotation, and the key thing is that an annotation. So we have an annotation. You annotate a type, a term as being of type tau. You can kind of there's a type that you're type checking the inner expression with, and a type that the outer expression has. And these two, whilst they have to all agree on the kind of the bulk of the type information, they have to they don't need to agree on the labels. You can have essentially fresh labels going in and fresh labels going out, and so they kind of break the sharing between the types. And that means that when you have something like this, so when we have this annotation, we have this. So we have f and we have a type annotation on it like that. This essentially means that there's no sharing between. You get to put. There's no sharing between the type that's going on into the context with any other labels, and so you kind of get to put. You get to generalize that information, and then so when we get to the call site, it will be general. It'll be generic, and we will know that we can apply the application rule. Right. Yes. So as I say, yeah, this is I'm calling this label type. So this is the main kind of underlying idea of the semi-explicit first-class polymorphism paper. And it's how ICAML has had polymorphic methods for a very long time. Kind of say a bit about how it's kind of implemented. So in algorithm J, unification variables are represented by mutable state. Right? Mutation is the easiest way to implement substitution. And so the identity of a variable is essentially it's kind of its physical address. That's kind of how you can think of it. And so adding labels to arrows means kind of doing the same for arrow constructors. Your arrow constructors are now mutable pieces of state. When you unify one arrow with another arrow, you have to mutate one to point to the other. And so your type expression is really becoming a graph rather than a tree. There is sharing, and you are keeping track of the sharing. But ICAML was doing this for efficiency anyway. Before PolyML, it was already doing this. Jack's nodding. Yeah, okay. So there's already really in some efficient implementations this kind of tracking of sharing going on. And then the other aspect is kind of how do you implement the side condition. So, well, efficient implementation of the gen side condition that a type variable doesn't appear free in the context. Obviously, it would be terrible to go and iterate down the context and look for the variable. That'd be very inefficient. So what you do is you track the earliest position in the context that mentions the variable. So here, it's kind of like alpha is appearing all the way on the left, and beta appears one thing in, and gamma doesn't appear in the context. And this is represented as an offset, essentially. It's normally called a level. And so you just kind of associate this level with the variable. Like I said, the variables are mutable pieces of state. Now they have a mutable field that's their level, and that's kind of this offset into the thing. And certainly in a camel, they use a special level infinity, essentially, although it's actually, I think, 100 million. So don't make too big a context, I guess. That represents that the variables that have been generalized. Right, and so doing the side condition on our for all, we have to do, the side condition on our application rule is basically, the side condition on our general means, again, putting levels on these arrow constructors as well, and tracking where in the context the arrow constructor might appear. But again, Camel was doing that for efficiency anyway already, because if you track the levels on the constructors, you can do more efficient generalization instantiation, because you don't have to go looking for you don't have to search all the way down to see if there are any variables underneath them, because there's an upper bound of the level of the things underneath it, or possibly a lower bound. I can't remember which direction. Right, so putting it together. So yeah, the underlying facilities were in a Camel even before polymorphic methods. Polymorphic methods use these to implement labeled types. It's kind of type graph view. And this forms the basis of a lot of a Camel's features that go beyond Hindley-Milner. It's very, like, being able to inspect a type gives you a lot of, lets you do a lot of things that you might not otherwise be able to do in a kind of principle-ish way. And so, so it forms the basis of a lot of those things. There was very little to do to repurpose this for polymorphic parameters. It was, about 6 hours from realizing it was easy to do to a production-ready implementation, which we rolled out into Jane Street, and it's been used for about a year. There have been no complaints, so either it works very well or no one is using it. It's kind of hard to tell the difference. So now kind of shortcomings and related work. So the first thing is this is very much not first-class polymorphism. This is still second-class polymorphism. We have not merged the type and scheme languages together to allow schemes to appear freely everywhere. You can't have like a list of identity functions or things like that. They're just appearing on the parameter position. There is eta expansion. We don't have simple eta expansion for functions with polymorphic parameters. So if you have a function with polymorphic parameters and you write the naive eta expansion, it just doesn't type check because it's a function with a polymorphic parameter that has no annotation, so that's not allowed. You have to annotate the lambda. This bothers some people. I kind of think it's fine. Eta expansion is a typed operation anyway. It's supposed to be typed. You're supposed to do this, but yeah. No inferred introductions. So it's demanding that every polymorphic parameter have an annotation right on the lambda. Whereas you might have that information via other means. So here is like with ID that says it's going to call the function and pass it the identity function. And so here, like this won't type check at the moment because this is supposed to be polymorphic and it's not annotated. We need to add the annotation. Now, actually, that's not what my implementation does at all. It type checks the first thing fine. A camel does some kind of bidirectionalish pushing around of this labeled information. But I don't think there's a formalization of it. It's not immediately obvious how to write the formal rules, so I didn't put it in here. But the implementation is kind of obviously fine. So. Related work. Yes, so there's kind of two groups of related work. There's kind of higher rank polymorphism work and full first class polymorphism work. So the higher rank polymorphism, there's that's where polymorphic types are only supported as part of function types, like in this. There's kind of Adursky and Laufer and Peyton-Jones et al. And that's the kind of the work that supports the rank n types extension in Haskell. There's also work by Dunfield and Krishnaswamy doing a kind of a bidirectional approach. And both of these are, the key difference there, both of these are predicative. So they're not putting the sigma into the tau at all. They're adding another arrow in the sigma that allows sigmas. And so that's slightly less expressive, although perhaps not, it is a perfectly reasonable way to do it as well. And then there's the first class polymorphism work. There is a lot of literature. This is a big space. I think that I kind of split it into three kind of classes. They differ mostly in how whether they infer the presence of instantiations, which is kind of the hard bit. And so the first is the group that kind of just don't infer the presence of instantiations, really. So there's QML, where just literally everything is annotated. PolyML, which is the kind of the one we've been describing here, is kind of semi-explicit. And FreezeML, where you kind of indicate whether you want instantiation or not in the term language. And then you've got this second group, which is where they kind of locally infer the presence of instantiations here in the kind of like local type inference sense. So they're not doing like, as opposed to the global type inference of like Hindley-Milner. So they're doing something normally kind of, it's normally kind of bidirectional in nature, and they're looking around the application site trying to detect whether they need the instantiations. So this, so there's HMF and then this little series. These four in a row are essentially trying to get impredicativity to work in Haskell, the impredicative extension. My understanding is that Simon is finally happy with the last one, but these are yeah. But I think it is fair to describe all these as somewhat complex. There's a lot going on, especially in some of them. Then the last group are the ones where you globally infer the presence of instantiation. So that's MLF and then HML, which is just a slight restriction on MLF. And they have the kind of the most terms work. And it's very clear where you need annotations. But in order to do this, in order to do kind of global inference of whether things are instantiated, you need to extend the type language to kind of be able to represent things where you have not yet worked out whether there's an instantiation or not. And that's this kind of like, so they end up with a kind of bounded polymorphism on schemes, which is, which is perhaps complicated for the user to look at. Right, so in summary, polymorphic parameters can be sorted using the same techniques as polymorphic methods. Labeled types allow kind of a principal inspection of type information. The implementation of labeled types is similar to efficient implementations of classic Hindley-Milner. Right, that's all. Thanks.
Some questions?
Yeah, I guess I'm still a bit confused to what degree impredicative types can now be inferred, or like,
Sorry.
To what degree impredicative types can be inferred now? That wasn't really clear to me. Like, because you just seem to allow sigma to tau as a regular
type,
right? So that
would
imply that you can infer it everywhere.
You can certainly infer it everywhere where you're not introducing or eliminating it. Like once for alls are guarded underneath something, they behave pretty well. It's only when they're unguarded that you get into a lot of trouble. So it's the points where they unguard and guard that you need some kind of annotation. And on the one side, we have the introduction form where the annotation's very directly right on there. And then the other one, we're essentially doing some work to kind of only do it when there is an annotation, but the annotation doesn't have to be like right on the thing. It can be coming from the definition or an annotation and then so on.
That was kind of my other question, because I was trying to make the connection to 1ML, right, which also can handle these examples, but that has a very simple thing where you just, like, if you have a binder and you don't type annotate it, then you put in an inference variable, and that can only be a quantifier-free type, essentially. So
yeah, I mean, I think the nice thing here is that if I write a function that you can get information if you just write you don't need a type annotation if you just like write a definition that uses polymorphism and then just generalize it. You know, there's a lot of examples where you have to do fewer annotations than if you just literally say you always need to write an annotation. This is really kind of like capturing a bunch of easy cases from there. There's maybe one way to look at it. Yeah.
Thanks.
Hey Dan.
Thanks. Hey, great talk, Leo. Always enjoy your practical insights. Very nice. I want to make a little advertisement for myself, but for everyone. If you want to do impredicative inference, like the previous slide, I still think HMF strikes a great balance between simplicity and expressiveness. So I would encourage anyone to look at it. And I had a question about your previous one slide back. You had like the drawbacks or the shortcomings.
Oh yeah.
But this right. The no inferred introductions, that's a strength. That's great. You shouldn't try to infer like the
I like
ID5, ID6. You do infer it?
Yeah. In this case, there's some amount of kind of bidirectional type flow inside the Camel's type checker where it kind of pushes this information in, and you can kind of like when the
So but if I would be Didier Remy, I would be furious now because your declarative system wouldn't capture that, right? You kind of accidentally infer something. But it could maybe rewrite it a bit, and now you don't infer it, right? So there's a risk that later, if you want to improve your type system,
it works. It's fine. It just
It's-
like
yeah, it's
like there's a big difference between have not formalized and like isn't principle. It's kind of it's only tricky because here the labels are kind of being treated like they're like a for all, and we're much better at doing for alls. The pushing in is a little bit like treating them like an exists. Exist is slightly trickier, but it's still
right.
It's kind of fine.
No, I'm playing
Anyway,
devil's advocate.
that bit was already in the compiler. You should really talk to Jacques anyway.
Okay. Sorry.
Let me defend Leo here. So in this middle example, right, look at the call to with ID, right, and with ID's type. So with ID says what type its parameter is. So all you've got to do is push that down. There's no danger of it being unpredictable. Yeah. You can absolutely write these down as just bidirectional type. This is what GHC does. Well, completely fine.
Sure.
So and then sort of generalization will happen. But yes, of course, in any bidirectional system, if you let bind, different things are going to happen. But that's different to saying it's unpredictable, right?
Yeah.
You can certainly predict what's going to happen. It just doesn't survive
really,
certain transformations.
It really is fine in practice. I know that this rule works very well in practice because whilst people don't use this very often, this is also how type-based constructor disambiguation works in a camel. And it has that exact problem. If you lift it out of a call, you have to add a type annotation. People still just think it's great. So like it just, like you said, that transformation doesn't work.
All agreeing furiously, that's good.
Okay.
So, Leo, do you actually have the typing rules written down?
Yes.
I mean, all together on one sheet of paper?
I do.
Great.
I had them in an OT file, which I lost, but I have the PDF still. So as long as no one asks me to change them, it's fine.
Or the PDF to OT converter.
Yeah.
Maybe let me have it?
Oh, yeah, sure.
Well,
Yeah.
I don't understand these labels
I
at
will.
all.
I will point you to where they are on the internet after this. Yeah.
Well, I just wanted to check. So basically, is it correct that what you did was essentially polyML with the special case where the asymmetric case. So what you added is the asymmetric case where you have sigma to something else.
Yes, that's right.
Putting the label on the arrow.
Yeah, and that lets you put it kind of lets you put the annotations kind of on the other direction than on polyML.
The problem in polyML is the label would have been of the sigma only, and then since it's not monolithic with the arrow, you cannot say.
Yeah. Yes, that sounds right. Yeah. I don't call it polyML. I mean, I did in this, but like, yeah. All right, super. Thanks. Oops.
I mean, something about memory and resources. And it would continue and continue. Even was Leo talk was something about memory management on the type level. So, I mean, that's kind of the underlying theme. And the first talk of the session by David McQueen about standard new pretty printer library for the standard ML.
Okay, can you hear me in the back? The microphone's working? Okay, so now for something completely different and rather simpler, I think. Why did I want to write a new pretty printer library? Well, basically, I had been using the pretty printer library that has been distributed with Standard ML of New Jersey for the last 20 years or so, and I gradually became more frustrated with it because I found it required too much trial and error to get the results I wanted. And so I decided to look into pretty printers, and so I went back to Oppen and surveyed the literature. And so I have a very simple, pragmatic goal, which is to have a better pretty printer for my uses. I want something that's natural, simple, predictable, and a fairly transparent model. And this is more specifically with respect to PP, which is the name of the pretty printer library in Standard ML of New Jersey, and which is derived from or based on the design of the format package in OCaml, which is again heavily inspired by the PPML pretty printer meta language that was developed in the 1980s at INRIA. Okay, so I want it to be expressive enough to be able to write the pretty printers that I typically write. And so, of course, one of the first things I ran into was that in the Haskell world, there's the Wadler-Lyon pretty printer family. And so I investigated that, going back to the Hughes 1995 paper and the Wadler 1997 paper, and the source code of the current library, and so on. And that's an improvement, but not quite enough. I found that the algebraic development technique led to an algebra of pretty printer constructors or document constructors, which is not quite as natural and simple as I'd like, and I thought I could do better. So this is an advertisement as usual, not a tutorial, so it's going to be rather fast and possibly esoteric to those of you who haven't recently fooled around with pretty printers, so I apologize. So Derek Oppen in 1980 wrote probably the first kind of general paper about a pretty printer engine, and it was completely imperative. And it was done in the context of the computing of the 1970s, 16-bit computing, and so he was very concerned about the length of the queue of commands that the pretty printer could manage. And so the main algorithmic result was that he could limit the queue length to 3 times the line length. Okay, but that's if you're working in some subset of 65 kilobytes. In the 1980s, as part of, or possibly in conjunction with the Centaur project at INRIA Sophia Antipolis, the PPML language, meta language was developed, and this had some new ideas. The idea of boxes, which was basically inspired by Knuth's boxes in tech, and the idea of conditional line breaks, which were also implicit in Oppen. And the boxes could have an alignment property, so alignment was another idea. And then Hughes and Wadler in the mid-90s, the big idea was that there would be an intermediate data structure that they called a document. I call it a format, which you build. So the typical thing in Oppen was that you had some kind of annotated text with some kind of annotations that might impose some kind of block structure on the text. And so you're going from text to text. And in most pretty printers, we're interested in having some data structure and printing it for diagnostic purposes or whatever. Anyway, another aspect of this, so the document idea as an intermediate structure is the main thing. And then Hughes in particular gave this as an example of a serious algebraic development of an algorithm. And that's nice, but I'm not convinced that the algebra that he derived was the most natural and intuitive. And of course, this was done in the context of Haskell, so lazy evaluation was invoked as part of the algorithm because it's basically generate all possible layouts and pick the best one. And generating all the possible layouts might be expensive if you didn't use lazy evaluation, but I and several other people have managed to translate the Wadler algorithm into a strict form in standard ML, for instance, and so laziness is a kind of red herring. It's not necessary. Okay, so this is just a picture summarizing the two models. With Oppen, he was trying to save space, so he was generating pretty printed output as he consumed the input in an online style. And the print engine was entirely imperative. You're basically generating commands that the print engine would execute. In the Hughes and Wadler model, you have a two-stage process where you first write a formatter function which takes you whatever data you want to print and turns it into a document or format, as I term it. And then there's a rendering function that takes that format or document and generates output, or possibly some layout representation that might be a data structure, but basically, what you're going to see on the screen. Okay, so I'm mainly interested in generating or writing pretty printers for a bunch of data structures, which are typically, in my case, abstract syntax trees, types, module signatures, various intermediate representations in the compiler. And in particular, I'm not trying to develop something that will compete with typical textual layout utilities like Markdown, ASCII doc, LaTeX, and so on. So the main ideas are blocks, which are like boxes. They're basically either simple atomic pieces of text, which will be printed as such, or combinations, hierarchically nested compound things. And these in PPML were called boxes following Knuth. And I use the term block, which comes from Oppen's original paper. These blocks are formats, which in Hughes and Wadler were called documents. So another basic idea is that we have breaks separating at the lowest level, separating pieces of text. And the break is either a space or n spaces, or it could be a soft line break, which means that it's an optional line or conditional line break, which might be triggered if you're running out of space on the line. Or it might be a hard line break, which means an unconditional line break. And then there's alignments, which are specifications of how things should be arranged within a block. So there's compact and horizontal, which are basically horizontal arrangement, but compact puts no spacing between the elements, whereas horizontal puts a single space between them. Or vertical alignment, or packed, which is you start filling in the line, and when you run out of space on that line, you return to the beginning and fill in the next line, and so on. So it's like a paragraph justification. And so one of the things we have to do is determine whether we're running out of space on a line. So that's the fundamental conditional driver. And so we need to know how much space the next thing we want to do is going to take, and whether we have room for it on the current line or not. So that I call a measure of a block or a format. And I've got to keep this awake. Okay. So the measure of a block is going to be very simple and very conservative. I just measure it as though it was going to be laid out on a single infinite line, suppressing all line breaks, even hard line breaks. Okay, so that's a very crude and conservative measure, but in practice it seems to be okay. And then another point here is that we're in the process of filling in a line. And so we're basically looking at the current line and the things to be coming up to be laid out on the current line until we have to go to the next line. And of course, once we go to the next line, the current line is finished. And so it's a very narrow, one-dimensional view of the arena in which we're playing. So here's some code. This is the definition of breaks, alignments, and formats. So breaks, as I mentioned, are hard, soft, space, and a null break for completeness. Alignment is C for compact, H for horizontal, V for vertical, P for packed. And then a format is defined by these 7 constructors. The primitive formats are empty and text of string. Okay, so those are atomic. Then you have 2 flavors of block. You have a general block, or basic block, which is just a list of elements where an element could be a break or it could be a format. You know, there's missing union data type for that. And so in that case, the breaks are explicit in the definition of a block, and you can put them where you like and what flavor break you want to, etc. So this gives you kind of a free form way of constructing blocks. But most of the time you're going to be using aligned blocks, where you specify just the format list and an alignment, and the alignment determines an implicit break between the elements. So if I do an A block with alignment compact, that means that there will be no break separating the format elements. They'll be just laid out contiguously. And so on with the other alignments. And okay, so a critical issue is indentation. So this is where Hughes and Wadler are both weird and unnatural. And so I just wanted to have a simpler and more obvious notion of indentation. And so I say, if you have a format, you can indent it so many spaces. And that indentation applies to the entire format, not only the last all but one line or something like that. So indent is just a modifier of blocks, of formats. And then there's another modifier called flat, which is just saying that no matter what's in this format, I'm going to lay it out flat. By laying it out flat, I mean I'm just going to string the individual strings or text items out on the line horizontally. So it's a kind of brute force flattening. This corresponds to the group function in Wadler. And then finally, so we have one source of conditionality in that we have these soft line breaks, which can get triggered as you're running out of space on the line. The other form of conditionality is this alt. It's basically an OR for formats, and it says if the first argument fits, lay it out. If it doesn't fit, try the second argument. And you only get 2 chances. Okay, so this is just a very schematic picture of what a laid out format. This is not the format per se. This is a particular layout of it. And the kind of reddish little boxes correspond to triggered line breaks, soft line breaks that are triggered. And there may be others, but only the ones that are triggered are displayed here. And then the blue boxes are hard line breaks. And there's, any block will have a left margin, which I call the block left margin. And overall, this RM is the right margin, and that's determined by the line length parameter that's driving the whole thing. The global parameter is the line length. Okay. Right, so conditional rendering again. At a soft line break, which could be like an ordinary block with a soft break in it, you're basically going to measure the following format, and if it fits, you just continue, or if it doesn't fit, you break the line and start on a new line. Now, when you break the line, you start indented to the current block left margin. Okay, so block left margin during rendering, the rendering process is a kind of part of the state that is maintained. The other one is if we have an alt, there's a function form of the alt constructor, lowercase alt. And if I have a format of the form alt format 1, format 2, as I said, we render format 1 if it fits, and otherwise render format 2. So that's it. As I mentioned, this flat measure is a key idea. We can get away with this really crude, conservative measure of the next thing to be printed, the next format. And the other point is that also to keep things simple, I'm assuming I'm worked in a monospace font. Even if there might be UFT8 character encodings or something like that. There's a device that's added to deal with UFT8. UTF-8? UTF-8, something like that. And so all the measurements are just in character counts. That's another place where we don't have to try to follow LaTeX and be fancy about measuring things. So the indented format, the two things to thing is that the indent operation is just modifying an existing format. It is not a format on its own. And indentation is activated only when you're starting on a new line. In other words, after a line break. It's basically doesn't really make sense to indent something that's going to be printed in the middle of a line. So indentation is inherently a property that only makes sense after a line break. And so that's reflected by that rule. So an example, in Wadler's papers, he has a couple of variations on printing a tree data structure. So this is a very simple data structure. N is a node constructor. Node has a string and a list of list of trees as children. And we format it using these two functions. So C block creates a compact block with no separators, no breaks. And here I'm using some of the interface of that the library provides is fairly rich. We provide a whole bunch of functions that people would have to reinvent on their own as soon as they start writing a pretty printer. And so to prevent that, we have things like brackets, V sequence, which is a vertical sequence, taking a comma format, which is just a text format with a comma in it. So it'll print these formats vertically, and with each format followed by a comma. And so that makes it pretty simple. And then I use map over format tree to get the children formats. And here's an example of a particular tree 1. And then if I format that tree and then call the top level print format new line, it'll print that. Okay, so I won't expect you to completely absorb the code in the example online, but anyway, that's a fairly trivial, simple example that shows you how it works. And it works quite well as you scale up to real-life examples. Okay, so at the moment, I need more experience. The main experience here was that I developed this library over about 10 plus iterations. And I have re-implemented 11 non-trivial pretty printers, like for types, abstract syntax, the Flint intermediate representation, CPS, flow graph representation, et cetera, et cetera. So there's a bunch of not non-trivial pretty printers in the system. So I re-implemented those using this library, and that worked. And it's a pretty straightforward translation because the structuring notions that come from PPML that are built into the older PP library translate naturally into these vertical, horizontal, packed block structures. And we need further testing and tuning, which is why we want to get this out to the world and get feedback from external users. There's a couple enhancements. John Reppy's version of the pretty printer was similar to the OCaml format, but he added style text, which is basically the main way of thinking it is you're printing to an ANSI terminal, and there are certain character codes you could send to the terminal that turn things red, or italics, or bold, or blinking, or whatever. And so there's one model of style text which allows you to produce interesting looking text on a ANSI terminal. There's another way of, in my case, a separate renderer that can translate into, say, HTML. The current case is it translates it into HTML3. But it could be updated to use HTML5. Then there's a variant of a text string, which is called a token, which allows you to put in a string with UTF-8 encoding, and then separately specify how many, what its length and character count is when it's printed. So again, we're still assuming in such a case that we're in a monospace font. So there's a set of monospace fonts that allow a certain set of UTF-8 encodings. And then potentially, there's another way of controlling the conditional line breaking, which is a ribbon percentage. It says how much of the line should be text. It should no more than 50% of the line be text, and so that's a way of a secondary way of limiting the amount of space you're allowed on the line. And it's trivial to add that. I don't have that in the system now, but it's a trivial change. Another more interesting one is some kind of tabulation, basic setting tab stops and tabbing to them. There's a very simple way of doing that I haven't implemented yet. But then Sam Westrick, in his SML format tool, has a pretty printer that includes an idea of fancy tabs, which are called, lexically or statically scoped tabs. And so I want to investigate that. I suspect that is probably compatible with this design, and if so, it'd be interesting to experiment with that. But again, I need more experience, more examples to drive what's necessary in terms of printing expressiveness. At the moment, I've got a very simple system and it does what I need, but other people might disagree. Okay, so in conclusion, I've got a simple model with a few key ideas: nested blocks, alignment, conditional line breaks, indented blocks, and a very simple implementation. It's purely functional, written in standard ML, quite small, and no need for laziness. Of course, eventually things go off to some device to be printed and imperative stuff happens. Is it efficient enough? I think so, but my impression is that it's basically a linear process. You have a data structure of such and such a size. You translate it into a format which is roughly linearly related to the size of the original data structure. And then rendering is also essentially linear. Again, because your scope of look ahead is very limited. You're just looking at how much space have I got left on this line. That's not a whole lot. The other thing about efficiency and optimality is this is producing human readable content. Something you're going to display in a terminal or a page, and you're not going to generate 1,000-page long pretty prints. You're mostly going to generate half a page pretty prints or 1 page pretty prints. And if it gets too big, you resort to some kind of depth limited printing, which was invented back in 1975 or so at INRIA. Just cut off the printing of the structure at a certain depth. As I said, it's a simple batch of code, easily ported to whatever. Question? Oh, wait. One more important slide, if I can. This is where you find it, and the source and documentation, including soon a fairly substantial tech report with a lot of background and details and so on. Questions? I'm a little bit over.
One quick question.
Hi.
Sam, by the way.
Oh, Sam. Hi. Yeah. Nice to meet you.
So when I was developing SML format, I ran into all sorts of interesting challenges for doing pretty printing for a full-scale programming language. Mm-hmm. And obviously your use case is a little bit different here, but I'm just curious, do you think that this technique that you've developed could scale to printing an entire grammar for, say, standard ML or a full-scale programming language?
I guess so. I don't off the top of my head see why not. Again, a lot in the very earliest days, the idea of pretty printing is that you had, say, a Pascal program, and it was laid out poorly by some student, and you wanted to put it through a machine that would relay out the Pascal source code in a prettier way. And you could do that with SML code too, but then you might be dealing with larger quantities of input than is typically the case in these cases I mentioned. So that remains to be seen, but I'm guessing that it'll handle it.
Okay, let's think again.
Okay.
As a reminder, so we can continue the discussion can continue on the Discord channel. So if you
Oh, with Mike.
Okay, so the next talk would be the second talk would be online, and you would introduce the first talk.
Thank you, Oleg. Thank you, Oleg. So I'm Dan, and I want to introduce Elton Pinto here. He wrote me about a year ago that he would like to do his master's project on a Perseus backend for Camel. And I always want to help students, so I highly discourage him to do this, because it's way too much work and too ambitious. So I spent a month doing that, but Elton persisted, and now here we are, and he's going to report on what he did over the past year. He's working now for a company, but I think next year Elton will go to UPenn as a PhD student. Take it away, Elton.
Is the audio fine? Or? Okay. All right. Hi, everyone. My name is Elton, and thank you, Dan, for the introduction. And I'll be presenting Exploring Perseus for OCaml, which is part of my master's thesis that I worked on last year. I'm currently working at a venture capital, but I'll be starting my PhD next year. Cool. So in 2021, Reinking and G et al. Presented Perseus, which is a novel compiler-guided reference counting system with reuse. And one of the distinguishing features of Perseus is that it's garbage-free. So at any point during a program's execution, only live objects remain on the heap. The most well-known implementation of Perseus is in Coca, and the paper evaluates Perseus using Coca against programs written in other programming languages like OCaml, Haskell, C++. And it runs pretty good, so in terms of both execution time and memory usage. But therein lies the downfall of the evaluation. There's been no direct comparison between Perseus and other memory management schemes within the same system. So we don't know for sure how good Perseus is. So here's what we did. We implemented a prototype of Perseus in OCaml 4.14, x86 64-bit backend, and it completely replaces the garbage collector. So in all of the benchmarks we've run, the garbage collector doesn't run. Right now, we don't support exceptions in mutable references. Like it will compile, but it will leak memory. But every other feature of OCaml is supported. And we've evaluated this on the same benchmark suite as the Perseus paper, and the performance results look quite promising, so we want to keep studying this. The source code is available on GitHub, and if you want to learn more about the implementation details, you can find it in my thesis, which is linked in my website. So the rest of the talk, I'll first walk through how Perseus looks in OCaml, and then I'll talk a little bit about the changes we made in the runtime, and finally we'll get into the evaluation. Cool. So first, Perseus. So most reference counting implementations are scope-based, and they might hold on to memory for too long. So if you consider this example here, we've got, it allocates a big list, say a list containing a million elements, then performs a map operation on it, and then prints the resulting list. In scope-based reference counting systems, the drops get inserted at the end of the scope. So now, when you print the y's, x isn't alive beyond that point, but you're still holding on to both lists because the drop to x's happens after the print list. Perseus does things a little differently. So instead of reference counting being scope-based, it uses this notion of ownership in which the function takes ownership of its arguments and is responsible for invoking drop on them. So a neat consequence of this is that reference counting becomes more precise, and so you get the garbage-free property from that. So let's take a look at how map is implemented to see how Perseus inserts the reference counts. So this is a map function written in OCaml. So after running Perseus, it's going to insert RC operations as follows. So note how it drops an argument as soon as it no longer needs it. So in the cons branch, for example, x's is not used after that point, so it invokes drop on x's, but then x and xx are used, so it first adopts them and then drops the parent. So this is what Perseus would output, and while it seems all right on the surface, it isn't entirely efficient because there is a little bit of redundancy. To see that, let's inline the drop operation. So after inlining it, you'll see that if x's is unique, you perform a drop on the children and then free the parent, right? So in this case, you're dumping the children first and then invoking drop on the children, so the reference count remains the same. So can we do away with this redundancy? The answer is yes. So we push down the dumps into each of the branches, then the dumps and drops cancel out. And so what you end up with is this program. So if x's is unique, then you only invoke free and you're not performing any RC operation on the arguments, and that's the fast path. And if it's not unique, then you dump the children and decref on the parent. This whole process is referred to as drop specialization, and we've implemented both Perseus and drop specialization in the Lambda form of the OCaml compiler. So all of this works. But that's not all we can do with Perseus. Perseus also supports reuse. So in this program here, note that in the unique case, we free a node and then allocate it right after. Right? So we could potentially reuse the memory that's being freed. So Perseus does this by using a notion of reuse tokens. So instead of freeing the X's, it will return a reuse token that essentially points or tells the constructor to try and reuse memory if possible. So we modify the semantics of constructors to use the reuse token and allocate inline, or I guess assign fields in place, as opposed to allocating a new node, so you could reuse memory if possible. We haven't implemented this yet, but it's in the works, and I'll talk about it a bit more as we get to the evaluation. So now that we are familiar with Perseus, let's look at the changes we made to the runtime system. So OCaml is not reference counted, so the object header doesn't have an RC field. So we first had to bake that in. So here's how we did it. We just split the WO size field in half. WO size encodes the number of fields that an object has. So a consequence of doing this is now objects can only hold on to half as many fields. But we can still support the previous WO size by assigning a special field after the object header that encodes the actual WO size, but we haven't implemented that yet. You'll also notice that the color field is still there. We don't use it, but we haven't entirely removed it, so it's still there. Also, it's only supported on 64-bit systems as of now. Cool. So the next thing is we have to implement the primitives themselves. So here are some primitives that Perseus uses: dup, drop, decrement, is unique, allocation, and freeing. Dup and drop have specialized forms as well. So if you invoke drop, if you know that you're invoking drop on a pointer, say, then you don't need to check if the object is a pointer, so you can just directly access the ref count and decrement it. I haven't showed that here. But there are specialized forms. I talk more about it in the thesis. So one way of implementing these primitives is to write them as external C functions, because OCaml has a way to write external C functions that you can call from within OCaml. But let's try and understand what the implications of that would be. To do that, we need to understand the different calling conventions at play in OCaml. And to our knowledge, there are 3 conventions at play. The first one is the OCaml convention. So OCaml, unlike C, has a caller saved. Well, all registers in OCaml are caller saved. So a consequence of that is when you invoke a function, say f, right before going to the function, the compiler will have to spill all live registers. Now what this does is it makes exceptions fast in OCaml. So instead of having to unwind the stack when you encounter an exception, you just execute 2 instructions and go to the handler. The other convention is the C convention, and this comes into play when you invoke external C functions. So when you switch from OCaml into the C runtime, because all registers are caller saved, you don't need to spill any registers on the stack. And so switching into C is pretty fast. But in some cases, you want more control into which registers are spilled. And for that, there's a special convention, which is used by the bump allocator. So in the special convention, special routines like the bump allocator can tell the register allocator which registers it clobbers. So in that case, the compiler doesn't need to spill all live registers. It only needs to spill the live register if it's clobbered by the special routine. A consequence of this is if the special routine breaks the contract, that is, it clobbers a register it said it wouldn't clobber, then you would need to spill and restore that on its own. So what do? Let's say we were to implement the primitives as external C functions, right? That may result in poor performance because we may be spilling registers we don't need. And since with Perseus, RC operations are called more frequently, we don't want to pay the cost of spilling and restoring, right? So in this example here, if RC dup clobbers, say, a register R10, there's no need to spill racks in RCX, right? So you could just do away with that and just call RC dup and things will run fine, right? So what we need is a way to tell the register allocator which registers are clobbered by our primitives. And as I mentioned before, we can appeal to a special convention. So when implementing these primitives, we use a special convention and we tell the code generator that every RC primitive clobbers at most 2 fixed registers. We picked R10 and R11, but we could have picked anything else. In fact, OCaml sort of has R14 and R15 fixed as well. R15 points to the camel state. I actually forget which one points to which one, but they're fixed in the compiler. So we implement the fast paths of the primitives carefully in assembly, making sure we only clobber those 2 registers. In the case of dup, for example, my pointer, over here, notice that we don't clobber any registers, so there's no need to spill. But in the case of drop, which I've inlined there, we clobber R11. But now, for more complicated routines like recursive drop, we do want to switch into C because it's a little complicated to implement it entirely in assembly. So when we do happen to switch into C, we now need to spill the entire register state because we lied to the code generator and said we would only clobber R10 and R11, but we don't know which register C would clobber, so we need to spill everything and restore it. So we do the same thing for allocation as well, because we want fast allocation, since with RC primitives, they'll get invoked more often. So to do that, we use memalloc, which is a highly performant and scalable allocator used by Coca and Lean. The good thing about memalloc is that it has fast paths that we can inline. So here's an example of an inlined fast path. This is the free operation. So notice how it's very lean. In fact, the fast path, we can sort of run it in about 8 to 10 instructions. And those only include a single test instruction. Now, in case the fast path fails, we make the call into C using gcall over here, and it switches into the C runtime and invokes memalloc's generic free operation. So as I mentioned before, if you use a special convention, there is a cost to it, in that when we switch into the C runtime now, it's a bit more expensive, but we only pay this for slow and infrequent paths, so the cost is sort of amortized. So that's the primitives part. So in summary, we've modified the OCaml compiler, and we no longer need the GC. We can turn it off completely. So the next question we need to answer is, how does it perform? Right? Will it perform well? So to do that, we evaluated the OCaml GC with 2 variants of Perseus, one that doesn't turn on any optimization, so Perseus as is, and the second one which turns on drop specialization. The benchmark suite is limited. It's the same as that of the Perseus paper, and here are the machine specs. So before we get to seeing the actual graph, I wanted to show how the assembly looks like now. So on the left is what the GC OCaml would generate. So note how it mainly includes program logic. There is only a very little bit towards the end which actually deals with the OCaml runtime. It first tries to allocate using the bump allocator, which is only about 3 instructions long. And then if that fails, it jumps and calls the GC towards the end. But with Perseus, we're executing way more code. So there's all these reference counting operations peppered throughout the assembly. And so if you look at this on the surface, it seems as though we're not looking too good, right? Because we're executing more code. But the results actually show that we're not doing that bad, actually. So here, orange is OCaml, red is Perseus, and blue is Perseus with a drop specialization, and lower is better in these graphs. So note how we're doing pretty good in execution time, performing better than OCaml in a couple of the benchmarks, except RB3. Memory usage drops by half in cfold and nqueens. Cfold performs constant folding over a large tree. deriv performs a derivative over an expression tree. Arbitrary is arbitrary insertion, and arbitrary CK is arbitrary insertion with a shared spine. Another thing I wanted to highlight is drop specialization has a big impact on performance, as we can see in RB3. So the performance nearly improves by 2 times when we enable drop specialization for RB3, and that's because the reference counting operations are kind of expensive if we just do them naively. Another thing I did want to highlight is for 3 of the benchmarks, the memory usage of the GC and that of Perseus is about the same, which is a testament to how well engineered the OCaml GC is. It's quite impressive. Cool. So we had to tell this to ourselves quite a bit, actually. We don't want to get too excited because there's a long way to go. And so I just wanted to put that out there as well. So in terms of future work, the benchmark suite is very limited. So we want to evaluate this on a bigger benchmark suite so that we have more confidence in how the system runs. We do want to implement reuse analysis because we feel like it will improve our performance in some of the benchmarks like RB3. One thing I did forget to mention is the benchmarks are representative of memory-intensive functional programs. So it's not entirely bad, but we still want to evaluate it on a bigger benchmark suite. And then finally, we do want to support like the entire OCaml language, so exceptions, mutable references, and multi-core OCaml. We did look into, like we thought of starting with multi-core OCaml, like the whole implementation, but it wasn't officially announced yet, and we had trouble getting it to build, so we just went with 4.14 at the time. Yeah, so thank you for having me speak. Source code is available on GitHub. Thesis is available on my website, and we are looking for a student to help push the project forward, so help us with implementation and stuff. So if you're interested, come chat with us after the talk. Thank you.
So we have some time for the questions.
Thanks for that. So when you move over to multi-core or multi-threaded implementation, you're probably going to have to switch over your reference counts to atomic variables. And there's one operation in there in Perseus that was is unique,
yes,
which doesn't seem like that'll translate at all. So what do you think the performance is going to do when you start introducing? Like, do you have any ideas of what the performance is going to be like once you start introducing?
Yeah, we actually do use atomic operations for reference counting. Like we have a condition that checks if we need to go into the atomic case. In terms of how bad it will perform, I'm not sure because we'll have to see. But maybe you have a better idea. Yeah.
It's a great question, by the way. Yeah. So this happens in Toka too. It's a nice. What we do in this implementation is it's like a positive reference count. We just don't use atomics. And when things could potentially be shared between threads, we use negative reference counts. And then the test, then we do one test, then we switch to using an atomic operation. And it can only work if the language is static enough that you can detect when things can become potentially shared between threads. And it's the same how Lean does this, because it kind of requires this monotonicity of the reference count. So yeah, I can show you. Yes, and there's tricks you can do.
Great, Simon Peyton-Jones. Just a couple of two sort of standard questions about reference countings. By the way, I really like this work. It's great to experiment with this. One is, what about cycles? And isn't reference counting incompatible with the efficient bump pointer allocation that you described? And the second question is, you showed just wall clock summaries, right? So some of that wall clock improvement comes from the fact that we don't have garbage collection. Balanced again, we do have more overheads during mutation. And I wonder whether you measured those separately. Like if you said, suppose GC was free, then what would the comparison look like?
Okay. Well, for the first question, which was about the bump allocation being incompatible with RC, well, that's why we use memalloc, because it does have a minor heap and like it has a minor heap and a major heap, and so it's sort of similar to the bump allocation, except that it uses more instructions. And what was the first part to the question? I forget. Oh, cycles. Yeah, cycles are a problem. So I guess the way they handle it in Coca is the programmer has to explicitly break the cycle. So yeah, so you
don't handle cycles.
Yeah.
Okay. This is kind of like, yeah. Okay.
Yeah.
So also, the bump allocator is not used
in this work. Yeah.
He just showed it as an example for how the garbage collector. We just use memalloc, malloc and free.
Okay.
Right. That is a great suggestion.
Measuring the overhead of garbage collector separately from the mutator.
Yes.
Yeah.
We have not done this, but it's a great suggestion. It works great as a baseline, and I think this is part of why we wanted to do this work to get better insights in how what is really.
It's like
how do they compare?
Yeah. So if DC was food, like how much worse would Perseus be?
Yes.
Okay. Thanks.
Hi, JJ, University of British Columbia. Really cool work. I was wondering. I was wondering with the zero garbage the zero garbage system that you have and doing the deallocations earlier. Do you lose any performance by doing these deallocations separately rather than if you have like a very large list with a lot of memory, doing them all at once at the end of scope? I mean, obviously you gain a bunch of more space and memory, but...
Right. So I think one thing that's neat about the bump allocated system is that it performs this optimization in which it coalesces memory in a pass, so it can like sort of allocate it in one chunk and deallocate it in chunks. But we don't do that in this system. And instead what we do is, like in the map example, if I can go back to it real quick. So what we're doing here is we are freeing the list as we traverse it. So there's no garbage at any point during execution, right? I don't know how much of an impact we would have if we just free the entire list at the end. I guess you would still have to iterate through the fields and free them, right? So I'm not sure. Yeah.
There is a benefit to cache locality by doing it right away. Suppose you have a really long list and you wait freeing it, and by the time you're at the end, you're going to free the list, you're going to trash your caches. But if you do it while you go at it, you win in the cache level. So sometimes I think maybe nowadays reference counting starts to work because it's so important to be cache local. But in the older days, it was too expensive to do the increments and decrements. One of my theories.
Do you have data to support that?
No data. I don't know, Simon. Right. Yes. So yeah, to be clear about that, there's real research there, like understanding why it looks like this. We don't know.
Anil Madhuripati from Cambridge, lovely work. I'm curious about how you might ever have. This thing is randomly turns on and off. I'm curious about how you might ever handle exceptions and effects, because they're effectively just long jumps that just go somewhere else, and the garbage collector takes care of cleaning up the system afterwards. So, is there ever an efficient way where a reference counter could work with exceptions that remain fast, as in OCaml?
I think we would have to take a hit, right? Because we would need to. So Perseus depends on knowing the liveness of objects, right? And so the way it inserts reference counts is it looks at when like a particular value is live, and then it inserts it like when it knows it's no longer live. So I feel like we will take a hit on exceptions. So, but I was talking to someone else the other day, and like exceptions in OCaml, I don't think are used in the same way as they're used in, say, Python. Like when you iterate a list in Python, right, there is an exception that's thrown saying that, oh, we're at the end of an iteration. But in OCaml, I think exceptions are thrown in truly exceptional cases, right?
So exceptions are, they are exceptions also.
Right, oh, they are, okay.
But effects are they really have to be very fast, because they interrupt that function.
Okay.
And they go back and forth.
Yeah. Yeah, I think we'll take a hit. Yeah.
So you're claiming garbage freeness, but it seems that your definition of garbage is what is kind of live, what is live, in the sense of not in the sense of what the computation actually needs for the rest, or the program needs for the rest of the computation. It's more like what is really traceable through pointers. So that might. I mean, you might actually do better. You might have something in the closures that are not going to be accessed for the last call of the function, and you might actually be able to decrease the count on those. So maybe you can comment a little bit on that.
It's a very good question, but
in some form.
The question is, what does garbage free really mean? Maybe we can do a little better. For example, are we holding on to things that are in a closure that you may actually never use anymore, like for the last call? It's kind of based on what's live means like what can be traced at any point. And it may not, it may actually, you could allocate some things maybe even earlier. So garbage free is a very technical term, like how we prove it like this according to calculus. And for things like closures, we actually, when you do the last call, we treat them as just like as with constructors. So we also drop as fast as possible. We don't leave something hanging in the closure. But you're right. There's a traceability aspect, right? It's like what you statically can see will be the last use of a variable. That's the time we drop. I think it would be very hard to do better than this. But you're also an expert, so maybe.
Well, okay. Well, that was the last question. Well, further discussion through Discord, please. And then, well, thank you again.
Thank you.
And actually would be a position paper by
Thank you.
Immutable arrays here.
Well, thank you. Well, this is, let's come to something completely different, not just in a Python-esque meaning here. So I will talk about, can you still hear me? Okay. I will talk about mutability, and I will just try to make a point where I believe that immutability is key if you really want to have arrays and fast arrays in your programming language, and that you should not give the mutability or the responsibility of the resources to the programmer. So the scenario really that all this is about to say if you're the programmer sitting there and you wonder, should I mutate or should I not mutate? That is the question. What should the answer be? And very often, you know, if you talk to a beginning programmer, it is a very simple answer. You say, oh my God, it's so complicated to figure out what the algorithm is doing and whether it is doing what I want it to do. If I don't have to deal with memory, please spare me the hassle. And then if you talk to students that have gone through the pain and have done low-level programming and have started to understand a little bit more what is going on here, they say, yeah, but you know, I have to deal with memory. My system has memory, and so I want control. You know, I'm not willing to give the trust to, say, even very smart people like Dan and Elton, right? No, I don't trust these people, let alone this Bodo guy. I really want to have the control, and then I can do much better stuff. And then if you start to talk to people from HPC, they are even more radical. Right? They most likely say, oh, you functional guys, you're completely nuts, right? I need assembly, because I need full control. And the point that I'm trying to make here is actually, yes, we can trust the compiler,
at least in the context of array programming. And immutability actually is a key to performance here. And that's the point that I'm trying to make. You know, no technical nitty-gritty details, but a couple of things that I have come across over time. Now, coming to something completely different. Sorry, it's not going to be ML, but it is a different programming language called single assignment C. It has some communality, minimal communality with ML. That is, it is strict. It looks like C, it feels like C, but it's purely functional. And if I say purely functional, I know. Many people will say, oh, but you don't have higher order functions, so it can't be functional. Sorry, no, we don't have higher order functions. If we would have higher order functions, we would try to compile them away before we even start. So, you know, you may envision that we have some form of higher order function, like higher order function in food talk, and we just would compile them away, and then you end up with a language like this. And purely the reason was that we are really, really interested in performance and parallel performance, high parallel performance. That's the goal. And we want to make it accessible to a wider public. Now, I always advocate and say, oh, it looks like C, it feels like C, and it behaves like C. That raises immediately concerns by the purely functional hearts in the audience and say, how is that even possible? Well, because I steal away the notion of memory. There's no pointer, sorry, doesn't exist. All data structures, in fact, are n-dimensional, immutable arrays. Okay. So instead of giving you slides and stuff, what I will try to do is I will run a Jupyter notebook here, if that is even, if I get my cursor back. Hello. That's a... No, I need to get that thing up there.
Is that going to show on the slides?
That's why I'm a bit... Oh, it's on the... Oh, I see. No.
Yeah, there. If you do that, that's not going to show there.
Yeah, I have the... No, it's...
Oh, you got it?
Yeah, if you... Where's some... Well, I should have tried. I have the preference manager there as well. Okay. So down here.
Ah, perfect.
And then I should be able to rearrange this, right? Most likely do something like...
Hang on, let me try. Yeah.
Yeah.
Where is the...
It's always the same. Sorry. I think...
mirror. Yeah, there. No?
No. I think you have to drag them. Yeah, there we go. Hey! Fantastic. Okay. So let's see whether we get this done. So, see if I have So I hope it's visible at the back. So we pretend to be REPL, but in fact we are not. So if you just whoa, interesting. In fact, if you just put in a scalar value like 4, then you will see that you get back something that gives you a dimensionality of an array and a shape, and it says, okay, the shape's empty, the dimensionality is 0, and the value is 4. Now, there you see, it is already kind of a little bit different. Now I can give you a vector of 2 elements, 1, 2. Dimensionality is 1, shape is 2, elements 1, 2. And then I can start, assigning things. I can, for example, say x is 1, 2, 3, maybe. Right, and once I've done this, I can look at x. And yes, it is what it is. Now comes the interesting part. I can also do something like x comma x. So it's now kind of a vector of a vector, which I write down. And you see it's a 2-dimensional beast all of a sudden. 1, 2, 3, 1, 2, 3. Okay. Now I can do an in-place modification. I can define a variable first of all. Let's define a variable y, which is this 2-dimensional thing now. So here's my y. And I can, for example, modify x at position 0 by 42, right? modify. Didn't I say immutable? That's weird, isn't it? So I look at x now, and x is, well, it is 4223. That's not really surprising. Now the interesting question is, will this have an impact on y? Hopefully not. And indeed, no. So you see, if I were to talk about memory, this would all be horribly difficult, right? But I don't, and that's very nice. And I can do really crazy stuff. I can, for example, say I want to select the first element of y. So you see, y is a two-dimensional beast, and I can still select the first element, well, which actually is the first hyperplane. So what happens here may occur to you as being very natural, and indeed I would agree with that statement, but actually what is happening behind the scenes is a bit more tricky, because we internally have an isomorphism between an n-dimensional array and an n-fold nesting of a one-dimensional. So by being able to doing these selections, you can switch between the nesting of the expressions that you have on the inside. Okay? And then you can define functions. So let me do one final thing. Let's define a function. And yes, we have some wonderfully weird types. So this is the return type in star. And in star means not it's a pointer to an integer. No, it means it's an array. And I don't really, it's an all quantified shape almost, right? So I want to define a function add that takes two parameters, a and b. So this is now two arrays of unknown shape. And I can return, and you see it smells like C, it tastes like C. And now what I want to do is I want to have an element-wise addition. Okay, that's fine. I say for any index vector, it's not, because I don't know the dimensionality. So any index vector, I actually want to select the corresponding elements in A and in B. And I want to add them up. And that's my definition. Right? So now I have an addition function, and I can actually write something like add y to y. And lo and behold, this has worked out. Now, if you were to define this in your resource-aware programming language, this actually is already very challenging. Why? Well, it is challenging because you would have to decide, where does the result go? Does it actually go into the memory of A or into the memory of B? Or do I have to allocate something fresh? And obviously, this could be an array that is a gigabyte large, right? Each of this. So that's a difficult choice. And to make matters worse, once you have made the choice, you have to keep this in mind. And whenever you apply this function, you have to think, okay, am I going to modify the first argument or the second, or, well, what does the function do? Or you may have to have three variants of this function. Oh, so from a programming perspective, I hope this kind of explains why I would really like to have immutable arrays. Now, to show you the rank polymorphism, so the ability to define this kind of function that takes any dimensionality, we can do something really funny. We can say we want to add up the first row of y and the second row of y, and hopefully this gives us 2, 4, 6. All right, so we can play with these things arbitrarily, that gives us a lot of expressiveness, of expressive power. So coming back to here, we go dark. No, we don't go dark. So what I will try to do in the remaining 20 minutes or so, or maybe hopefully less, I will explain how we achieve these three goals and how they interplay with the mutability aspect of the language, or more precisely, the immutability aspect of the language. So I will start with the productivity aspect, and that is essentially the power of rank polymorphism. So if you would ask me why I believe in rank polymorphism, I used to say until, I don't know, 5 years ago, it's genericity. Oh, you can define operators like this add, which can be applied to any dimensionality. So you can write way better algorithms because you can combine things without having to explicitly say something about dimensionalities or sizes. It's just more powerful. You can write APL-style code. But as of recently, it has become much clearer to me that the real power of rank polymorphism actually lies in the ability to reshape arrays. What I mean by reshape is, you know, if you have a vector of 16 elements, and you have seen this, no, I haven't shown you that. If you have a vector of 16 elements, you can look at it as a two-dimensional matrix 4 by 4, or at a four-dimensional array of shape 2 by 2 by 2 by 2. Now, what is that good for? Well, I will show you. So here's one example that we have investigated kind of last year or the year before, scans. Well, it's a simple mathematical problem. You have a vector of elements, Aj here, and you want to compute a new vector of the same size, and at any position I, you just sum up the prefix of this vector up to that position. And we start with a 0. For that reason, now we put this into code, and we are stupid beginner programs or unexperienced beginner programs. So we say, okay, we take an n-element vector here as an argument, and we return two things, an n-element vector and a number. And then what we say at any position I should have called this j here, I have just mixed them around, we sum up all the elements aj as long as aj is smaller than ai, and then I. And we do that up to all the elements, and finally we return the sum of all the elements. Easy, huh? So why do we need more than one dimensionality? It's just a vector problem. What the poop is this guy talking about? Well, now I have to put on my high performance hat, and then I immediately have headaches. You know, I tell people you can write as you want, you know, put your math into code. Beautiful, isn't it? But if I compile this into code, then what I see here is these things, these curly brackets, or tensor comprehension as we call them, they are implemented in parallel. Oh. So we have n summations that are all done in parallel now. Oh, this is horribly inefficient, right? Because we have no sharing whatsoever, but we have concurrency all over the place. Oh, damn. So now, the devil, the second argument of my initial programmer, will say, ha, see, told ya, right? I need control. Okay. Let's think what we can do. So first thing we can do is we can say, okay. We can have a sequential implementation. After all, what looks like C works like C, right? So here we go. You just use a for loop. We can do this. We iterate over the shape of A, well, which is actually n here. And then we, you know, do updates on A. And we trust our system. Immutability means, you know, the A that we have here is replaced by a new A for the next iteration, so that is fine. Okay. But then my performance hat again gives me headache, because here we have now maximal sharing, but no concurrency. Oh my God. Oh my God. So it seems actually we can do something like concurrency engineering straight away. So, okay. If we can do concurrency engineering, let's do this. So we have a vector, and then we turn this into two chunks. And because our universe is n-dimensional, here we say, okay, we make it a two-dimensional matrix, which is 2 by 4 in this case. And now we can have our sequential scan operate on the rows. Okay? If we do that, it looks like this. Well, because we have the sum before the zeroth element, the first element is always going to be 0. So here we see 0 and the 0 plus 1, 0 plus 1, 2. And then we have the overall sum of all these 4 elements. Okay. Okay, how do we get to the overall result? Okay, let's have a look. It looks already kind of good, but this sum needs to be somehow added down here. And if we would have multiple of those, then we would have to add this for the next row. So what we actually can do, we perform a scan on this vector now. That gives us 0, 6, and 28. And then we use this vector to actually adjust our previous result. So we add this vector so that the 6s are being added down here, the 0s are being added up here. So we obtain this. And if we reshape this back, woohoo, the miracle has happened. We have our scan. Ooh. Now we are rank polymorphic, right? So let's put this into action. So here's the SEC code that does exactly this. I've given you the picture from the previous slide so that you maybe have a quick idea. So here, up here, here's the exciting part. We do the parallel scan over the rows, right? We pick an individual row here. IV is going up to M, so we either take the 0s or the 1's row. Then we have a recursive call. Recursive call. Ka-ching, ka-ching, ka-ching. Well, but this is just a call to the sequential version that we just had, right? Okay, so this is a sequential scan that is done in parallel. Once this is done, we do the scan over the MS values, right? And that gives us this vector MS here, which we use in order to adjust our A, and there's the result. Now comes the miracle. The miracle bit is we change this into a rank polymorphic version. So rather than saying this has to be 2-dimensional, we say, well, we actually, it can be larger. How large? Well, actually, I don't care. What this notation in red here means, it means this is an arbitrary prefix that has n dimensions. And the shape of the prefix is bound by the variable ship. And that's what we do. And the miracle is the other code remains unchanged, right? So what does this give us now? Well, it actually gives us, depending on the shape, a very different behavior in terms of concurrency. And it turns out that this contains almost all well-known formulations for scans, in particular, Blaloff's algorithm as well. If you're interested in those details, have a look at the Array'22 paper that discusses it. Now, the interesting point from coming back to the question of mutability is now, think for a second, you would have to deal with mutable arrays. Now, the recursive call that we make here is on a subarray. Oh my God. So sometimes I operate on an entire array, and sometimes I operate on a subarray. If I have explicit control over my arrays, I have to decide what to do. That means a single version like this is no longer sufficient. Oh, this is a bit of a nightmare. All right, moving on. Another example, I will not go through the details, is we can play a similar game when it comes to blocking. You know, we have been talking about caches. Thank you again, very helpful. So in order to do matrix multiply, for example, you want to do blocked algorithms. That means if you have a 2x2, a 4x4 matrix like this, you would actually like to look at it as a 2x2 matrix of 2x2 matrices, right? So you can achieve this blocking by just a two-liner, and then you have blocked matrices. Okay, what does this mean? Well, if we look at a matrix multiply, a naive matrix multiply, most likely all of you can understand it, even if you're not a sec aficionado yet, right? It's just an m by n by p, and we get an m by p back. You see a single tensor comprehension here. While not really, on the inside we have this is the scalar product, and this is just saying for all indices ij, we have this inner product. Now what you can do is you can say, okay, if you give me a blocked version as arguments, what I really would like to do, instead of having a multiplication here, I would like to have a matrix multiply there. So all changes are in red. I say, okay, this is bigger dimensional. Okay. And here I call matrix multiply recursively. The beauty of this is, well, this is a full implementation of tiling. What kind of tiling? Well, as many levels as you want. Why? How? Well, you encode the tiling in the shape. And again, we have a situation where the matrix multiply may get an entire array or a subarray of sorts. Try to do this when you want to handle memory explicitly. It's not going to be any fun, I dare say. So the real insight is you can have a tiled algorithm as a, 6-liner or 8-liner, and it's arbitrary tilings. You don't even nail yourself to one particular tiling, because the tiling is encoded in the shape, not in the code. And it only works because we have a shape recursive formulation here, which gives you a headache if you want to be explicit with the memory. Now, if you're interested in more details, we had a paper on FHPNC this year, and we actually show that we have blast performance competitive with MKL. Right? So it's multi-threaded execution, super high performance from this kind of specification. So, if I may have a quick fazit. If you have mutable arrays, then you have to make unpleasant choices. So you don't really want to do this. We saw it in element-wise addition already. If you have rank polymorphism, and you use rank recursive algorithms, you can write super powerful encodings. You can do concurrency engineering, performance engineering, all that without thinking about the memory, right? And if you want to do this with mutable arrays, it's going to be a pain, because you have to figure out whether you are dealing with a shared pointer or a non-shared pointer, who is going to release things when and why. So conclusion is, programmer productivity, immutable arrays, great, right? Well, there's many occasions where programmers wish to have certain things. The question is, can we deliver, ultimately? But my argument, so let me super quickly, browse, is think about optimization. I just give you two stupid examples. That code removal, right? So I give you this snippet, and generate is just allocating an array and filling it with some data. And then you have a call foo that takes A, and it returns an X, but you return A. Question is, can I get rid of this? Well, not quite sure, right? Because what if foo does something to A? If A was mutable, this could happen, right? But I have the guarantee A is not mutable, so I can just blindly chuck it out. Common subexpression elimination, same story. You see foo of A plus foo of A, okay. Ooh, if it's mutable, maybe I can't do a thing. I could have an analysis. If I have foo available, I could have an analysis and say, oh yeah, you're good, you can do this. But here I don't have to do that. I don't even have to think. I can immediately say, yeah, sure, I compute foo of A once and that's it. Because I'm side effect free. Immutability is, opening up the doors. Let's talk for a brief second about concurrency. So one of the cool things of this language is that these tensor comprehensions are inherently parallel. They are kind of map-like thingies. Now, if you would write this and you wouldn't know that A is state-free, then it's not even clear whether concurrency is admissible. Because if I do a side effect here, the order may matter. Oh, bloody hell. It would all go down the drain. So, essentially, it all looks good, right? Better programmability, better optimization, easier parallelism. Yay! But there's, as always, there's a but, and that is, how about destructive updates, right? Now, here I simply piggyback, on essentially the ideas of reference counting. Now, what we do is reference counting to the rescue all over the place. We only do reference counting, and if Simon still was here, I would tell him, no, we don't have cycles because we can't construct cycles because we don't have any closures at runtime, and we don't have any self-referring data structures. And what can happen here, even if we are very naive? Well, it could happen that when we call foo, there's more than one reference to A. So in the first iteration, it might happen that we actually have to copy A here. But once the first iteration is gone, all subsequent iterations can be done in place. And we figure that out. If you have a situation like that, we break up the loop, we do the first iteration with a potential reference count operation. All subsequent iterations we just do blindly as destructive updates. So there's a lot of related work that pre-exists. And, talk to these two gentlemen if you want to have further convincing that this is possible. So let me briefly conclude. So I would like to make a strong claim that immutable arrays, at least, are an asset, not a burden. Right? It is fantastic for the programmer. It is fantastic for the person that tries to optimize your code. It is key to get data parallelism, and it is key to get real HPC performance. And I don't mean linear scaling of something that is slow. I mean real, close to the peak performance of the architecture. And you can run the same code without any modification on various different platforms, from shared memory to GPUs, MPI, or experimental hardware. Thank you.
Very entertaining talk. Thank you. I really enjoyed it. One of the immediate problems that somebody might run into is when they do need fine control over memory. And maybe a concrete example of this would be, maybe I want to implement a high-performance concurrent parallel hash table, something like this. Is it completely outside of the realm of this programming model? Because I need to be able to say atomic updates and these sorts of things in order to do that data structure. And it's okay if it's outside of the model, but I'm curious, is it possible?
No, well, here in this model, the idea is because the only way to introduce concurrency is through data parallelism. So we have a clear control over that, and we can have a static inference of the lifetime of all our variables. So in that sense, there's not a problem. I would love to perform some research in supporting natively sparse matrices. For the time being, the way to go is use the same tricks that all the imperative guys use. That is, you have compressed row storage, say. That means you have 3 arrays that you use in order to do it, and then you can express all your algorithms in the same way. But for the time being, you personally have to translate your sparseness into parallelism, and into the dense representation that we have. Pleasure. Thank you.
That's lunch, and we'll continue after lunch.
You mentioned a couple of papers in the talk. How can I
Okay, so let's start the afternoon session with a talk by Martin Elsman about programming explicit effects in ArrayML.
Thank you. Yes, so this is the context here is effectful high-order programs, and the issue that it's quite difficult to reason about these programs, in particular the effects that may occur when you have mutability and other effects, exceptions, and so on. The particular context here is memory management and reading inference, but I just want to emphasize that this of course goes beyond that. But to begin with, we would like to make good use of memory, and in this context here, I'm going to talk about the ML-Kit, which has this region-based memory management model and uses region inference. And one of the questions there is it actually going to make good use of memory, or will there be too much garbage which is not collected at runtime? So that's one thing. And then once you start adding threads to such a model, you may ask other questions about mutation races, but also allocation races. Different threads might refer to different or to the same regions, and that means that when they allocate, they might race for the allocation pointer for that region. And then, of course, we would like also to be able to reason about whether some function will potentially raise an exception. And we can also ask whether a function will mutate any shared resources. So the in particular context has been here for combining task parallelism with in the context of ML, and there's been a lot of work on that. I'll also get back to other related work in the area later on. But in particular, I want to emphasize here that this idea of adding threads to ML raises a lot of questions about memory management, and that has been explored in the recent years. So a little bit, just a primer here on region-based memory management and region inference. So this idea of region-based memory management will allow the programmer to associate lifetimes with objects and values, and they do so through these regions. And that means that you will be able to reason about when they allocated these regions, when you allocate into the regions, and then when finally you can safely deallocate the regions. So in contrast to explicit region-based memory management, region inference is basically the task of inserting these annotations in the program at compile time. And then hopefully the inference algorithm will do a good job at it. But that might not be the case, of course. So there are programs that are just inherently dynamic in memory management behavior. And that means that you might not really know and get any static guarantees about the reuse or deallocation of memory. So in this context, we're going to propose an approach that kind of combines these two things, with being explicit or being implicit. So we propose this REML framework where you basically allow for annotations, but you also depend on really an inference algorithm underneath. And we're really just going to be using the model of region-based memory management and region inference that is implemented in the ML-Kit. So that model has the features that it organizes the heap into a stack of regions. So we have the region stack here. First, there's a region R0 allocated, and then it basically may grow. But after a while, you might still allocate into these regions that are lower on the stack. So R2 may actually increase in size. And the way that's implemented is by using a stack of pages, or free list of pages, sorry. And that free list may then efficiently be managed by the runtime system. Once you deallocate a region with potentially many pages in it, in a constant time, that free list will, or that list of pages will be augmented to the free list, and then other regions may make use of that of those pages that have just been freed. And then, of course, the idea is then that we have this region inference that we will take a program, and then we'll try to infer and associate all allocating expressions are then associated with region variables, and then there's this inference algorithm that will try to unify based on the type system, and then we will try to see when it can actually get rid of regions again. And the source language that I'm just going to give you, this was from back in POPL 94, where Tofte Talpin has this calculus of the lambda calculus extended with recursive functions. And then here we have extended also with this let spawn construct that allows us to have multiple threads working in the system. But this is a source language, and then there are possible annotations. So whenever you have an expression, you may wrap around it a let region construct, and the idea there is to allocate a region on the stack and associate that thing with a variable row here, and then within E, all allocating expressions will then refer to a region, and in particular it may refer to that region being allocated there, and then you can this will be the model for allocation. So here we see some expression annotated with an add construct specifying that there will be an allocation inside that row. Once you reach end here, the idea is, and that's kind of the goal, of course, of the type system, to guarantee that it's safe to deallocate that region at that point. And it's a region, and it's an type and effect system that will allow us to make that guarantee. So here's a small example. Let's consider that we have a language extended with pairs, and that integers themselves also go into regions. In real life, they won't. They will, of course, live in registers. But here, for the sake of the example, we see here an expression, let y equals, and then there's a let region construct. Two regions are allocated, row and row prime. And then we have a local binding to a variable x here. We construct a pair, which we save in row prime. And then there are two integers, 3 and 4, which are allocated in row and row double prime. So we see here that row double prime is global to this expression. And region inference has figured out that row and row prime can really be deallocated here at the endpoint. So what happens is that we construct a pair, then we extract the second component, and after that we can get rid of the regions occupying holding the pair and also holding the number 3 here, and then continue. Okay. So then the question becomes: so how do you actually extend this to a larger language? And the first thing that comes to mind is that it becomes necessary to add regions as parameters to functions, and because otherwise you will basically unify too many things, and one expression may have a particular influence on other parts of the program. So the way to go about it is to allow all functions to take regions as parameters, and then we see here a function f takes a row as parameter. It will just store a number 5 here in the region, and then locally it can call the function f with a row prime. But notice here that the row prime can be local to the context in which the application occurs. Whereas if you did not have region polymorphism, then different calls to f will mean that you will pile up this 5, several versions of 5 will appear in that region row. Right, so it's important to have the feature of generalizing over the regions. And then what we see here is that the type system will then allow us also to express this polymorphism in regions, which means that here we can see that it will put something in row, and so on. So in REML, we would like to basically make it. Well, first of all, I should say that a standard ML program is also a valid REML program. So we want to start with something, and then basically add annotations that will allow us to make certain that certain guarantees we have obtained also survive edits of the programs of various kinds. You want to be able to have it to behave as you have engineered it, even after changes to the program. So there's this one exception. There's a region declaration you can make here. So you can declare a function f, and then you can have a local region R, and now you can specifically say that we will store something in the region R. We can also decide to use a global region instead. There are some built-in global regions, and this is just the pair region of the global one. That they are kind of put into different bags of pages, and that's particular to make it also possible to combine with garbage collection, and then you have a very efficient representations of the different you kind of have tagless pairs and so on, and instead you use the regions to carry the tag of the value, so there's no overhead garbage collection wise for a number of data representations. That said, so there's a global region here, R0 pair, and you can specify and be explicit about that this function will allocate into this one. You can also, instead of annotating the values or the expressions where to allocate, you could also specify that the same thing using types. So you're allowed to specify that, well, this variable x here will be given this type int times int, but the result is going to be located in R0 pair here. Okay, and then we can see here after region inference and so on has been carried out, we can basically check that that this still holds, and we see here the result of the program. We also see something else, that region inference has taken care of other things in the program. For instance, that there's a region R15 which contains exactly one word, and that will be the pointer to a function. The function itself does not contain any free variables, which means that it will only be the pointer to the function itself being stored in the closure. So that closure is stored in R15. That thing is stored directly on the stack, and there's no need for heap allocation for those things. And then we have an immediate call here in this case, of course. And this is just, I must say here that here we have basically turned off optimizations and inlining. Of course, when that is turned on, you won't get this call. You just basically have the beta reduction here at compile time. So again, you also allow the programmer to express that the function can take regions as arguments. And what we see here is that you can write a function down that will then store a number of elements in an integer list. And really an integer list is, An integer list is basically just a pointer structure where you basically chain a number of pairs together, and then the pointer itself will be nil if or null if it represents nil, and otherwise it will be the pair itself with a tag saying that it's a value. So then we can see here that we don't really need to say anything about the body of the function. Everything is implicit in the body, but we have basically expressed that all the elements will be in this region, meaning that you will be creating a new region, or you will be storing things in whatever region you pass into down. Okay. So here we can see here that we can we can call down on the region R and a list of 5 elements, and then we can extract the first element, and then the region will be local. It's fair to say that the region can be local here, right? So we can get immediately rid of the garbage again. We can then have a different concept comes up, so you can ask and classify certain functions and specify that, well, you can call a function exomorphic if it in general stores its result in regions that are different from those containing the arguments. And here's one example, copy, which will take any list of arbitrary content, and then it will copy the spine of the list into a new list. And those elements of the second list of the produced list will be in R2, and then it will take the list, the original list, in R1. And we can see here that that copy takes 2 regions as arguments. And now, if we forget to copy here, we'll get a type error stating that well, we cannot just create a new const cell here, and then which should be in R2, and then use something in R1 for the tail. That is not that violates the type system. So that will be an error, and we see here the error message of REML will give you this. You cannot unify the explicit region variables R1 and R2. And here we use this trick also, which is basically comes from ML as well, that the type variables that are explicit never unify. So you're basically just using that trick here to enforce this thing. That doesn't mean that you cannot copy with in a particular context. You may use copy to actually store into the same region as the argument was. It just says that the function copy has that property that if you give it something, you're allowed to store it somewhere. The result will be somewhere else, or could be somewhere else.
Can I ask a quick question?
Yes?
So you annotate the list with the region, but what's the region of the elements?
The question was why don't we see any annotations of the elements here in the thing? That so the point here is that that substitution will allow us to use this function in any region context. So it may be that the regions will be the copy here will explicitly say that whatever you substitute alpha for will also be contained in the result list. So copy is a shallow copy, right? It's not deep. It won't do anything about the elements of the list. They will just be still the same pointers.
So the universe of the types that we substitute for alpha can contain region annotations itself, right? Like
yes. And they have to be the same in both the argument and the result.
Thank you.
Can I ask something as well?
Yes.
Does that mean that you need some kind of thing to say that R2 won't outlive R1 in case you get an element from R1?
So there's no outlives relationship here, which is very different from much other work on region inference. So here it's entirely based on substitutions. So there's no outlives relationship between regions, which is different from the monadic region approach and much work that has come after that, based on that, which is really using this outlives relationship, that one region needs to live longer than something else. But there's no such thing here. This is cleanly substitution. I get a little bit back into that. So we have the endomorphic functions on the other hand. They are like kind of functions that will like append, right? So they will it will store its result in the same regions as its argument, right? So here we see the append function. It takes some x's and some y's, and it produces a new list. Well, part of it is new, right? But it is required that it actually fits together with the list in YS, right? Because it may use that. We can see the implementation here that in the case that the x's is nil, we really return Ys. So that means that needs to be an equality between the type of the argument, the left argument, and the result. Okay, so if we need like kind of to make a real copy with append, we can still copy y's. Here's an example copy append, where we copy y's and then append that, or x's is then appended to the copy of y's. And then we can get the other version of copy that is of append that basically creates a whole new list. Okay. So there's also region polymorphic recursion supported. So of course in ML we don't have polymorphic recursion as such, but on types. But we do allow it on regions. And there's a very nice example here using merge in terms of merge sort, where the local calls to msort will use different regions, and for that reason we will really have local use of memory. So the way to write that function is that it's parametric in this region R. In the case we have a singleton, then we'll just store that element inside R. Right? It doesn't say that X is itself. That could be in any other region. So we're only explicit here about the resulting region, which also is kind of this idea that we can of course look at the region annotated version of the program, the inferred one, and there we can see much more refined region annotations on the program, including effects and all that, which has left us up to this thing. But here we are just being explicit about the result. So we can express this thing in REML here. The result goes in R. We have local regions R0, R1, and R2. We will split X's into two different, the left and the right version. And here these things will both go in R0. Okay, the split function will store new lists in R0, and it's important here that it's basically stores something distinct from where the argument is. So split needs to split all the way. It cannot just split and then return the two. Then its trick doesn't work here, and this is checked by REML. So then we can sort the left one, sort the right one, allocate the result in different regions. You see and here we see the polymorphic recursion here, because they use the local regions. And then we can merge finally the result, and the merge will then store the list in R. Okay, and we are done. Okay, so that's a kind of without using a garbage collector, we basically have, and it's not in place as we've seen other work here. It is of course using, or it is using memory besides the argument itself. Then we can be explicit about effects as well, and there's a special annotation here in REML. I won't say too much about that, except that that combines very well with expressing constraints on types. I'll get back into that here. So REML supports these kind of effect constraints where you can be specific about what kind of effects a function can have. So in particular, we have constraints of the form that one effect or two effects really contain no intersecting put effects. So they will store into different regions. This is a little bit different than Flickr, for instance, where you can say this particular effect you don't want. But here we also have the possibility of dealing with intersecting, restricting that we are not allowed for two effects to intersect. Similar for allocations also, and then we have this no mood construct, which will basically say you are not allowed to mutate, to have any external mutation going on. So let's see here an example working with a locally immutable storage. So we have here a region R. And we see here we store into that, we have a mutation on R here, and REML will complain. If we remove that assignment here, we can still have local state, and that will work out fine in REML. There won't be any errors, but otherwise you will get this mutation constraint violation. The effect E contains the atomic effect mutation on this global ref region. And then just to finalize here, this idea of doing parallelism is basically, so we have added support for threads in the ML kit underlying environment or framework here, and there's this inference that does protection inference that kind of try to identify whether two different threads will allocate into the same region. And if they will, then this region will be protected by a mutex, which then needs, and that means at the allocation point there's a big overhead to allocating into those regions. So that's basically, I think, what we specified here. I mentioned the let spawn construct, but with REML we can basically unlock this parallelism feature in the sense of specifying exactly what we need from the effects. So here we can say that the two effects associated with the spawn function here for each of the and this is the interface here given. Then you can specify that the two effects need to be disjoint using this construct. And then whenever you call it, you will get that check done. It might be that you can actually, should say here, you can write then the MPL version or the par function. And if you do so, of course, you can call it needs to call the spawn function as well to implement that. And then that will also have to carry a while constraint. So those constraints, they are really passed along for reasoning. So that's I should mention this is ongoing work. Part of the system works well already, but there's still some implementation to do. There's also a formal treatment of these effect constraints going on, and I want to emphasize there's a lot of possibility, of course, for adding other kind of effect types, mutation, we saw that, but IO, non-termination, and so on, whether something is pure. And there's a lot of related work out there. I just mentioned some of it here. But yeah, that's it. Thank you very much for listening.
Yes. Is it possible in REML to actually return a region from a function? Is it a first class?
It's not a first class system as such right now. This is something we could definitely explore. Right now we have this region stack. It's intertwined with the C stack in an implementation. So it would be great to have extensile regions and so on, and maybe some other mechanisms for working out with this.
These constraints you showed, the microphone. Can you? Yes. The constraints, they're always written explicitly by the programmer. Is that?
They are written explicitly when they are important. If you saw the spawn interface and the par function, and then they are checked if they're still. Everything is checked, but once you reach another effect variable, this is where there's no automatic inference going on. There you need to have, from the context, you need to specify it. But if you, for instance, call map inside something, all the effects there will be propagated automatically through the.
So I'm just wondering how this affects principality of type inference and so on. Does it? What's your correctness property for
type
inference?
soundness?
Yeah, for completeness. Do you have a complete complete type inference in the presence of these things, or is this sort of, are they sort of orthogonal layered on top of your usual ML type system?
It's on top of the, so maybe I don't quite understand the question, but let me say that there's, for any ML program, you can annotate, and there's a simple proof that you can, how you would be able to annotate.
I guess my point is you couldn't infer these things, I guess, in general. It's
no, you couldn't infer. So, of course, here you saw also REML would come up with an error if the constraint is violated. It's not that it will guarantee that then the regions will be disjoint. If it type checks, then it's safe. So if that was what you meant by completeness, yes, then as soon as you start adding these constraints, then of course the original, you cannot be guaranteed that the original ML program will actually have a type completion. Yeah.
Mm-hmm. Okay, well, let's thank Peter again.
Pierre Chambard. Is that okay? Yeah. Can you hear me? That's a good one. So I'm presenting WAS-OCaml, so compile OCaml to WebAssembly, or WASM, because, well, it's neither an assembly nor for the web. And so that's Leo's work, my student, but, well, he couldn't come here. You shouldn't let your students submit articles when you're not sure they could come. You will see me far too much in the next 2 days. And yeah. So why compiling to WebAssembly? Since, well, OCaml already has compiler to JavaScript, which works quite well. Because basically JavaScript has some problems when you compile to it, is that it's quite unpredictable in performances, and you generate gigantic JavaScript files that can take quite long to load. WebAssembly is a lot more compact and basically has always the same performances, and you should expect that the performance difference between different runtimes is going to be a factor between one or another. So, well, and yeah, there are some places where you can't run JavaScript, or just better to run WebAssembly. So, as Andrea told you, the basic first version of WebAssembly had things in there, but basically only what you want to compile C-like languages. And if you wanted to compile OCaml, you had some restriction. And it was quite hard to communicate with the environment. So what does WebAssembly look like? Something like that if you look at the stack syntax, but Andreas lied to you, it's not a stack language. It's an expression language, it's just different of encoding. And well, that's factorial in WebAssembly, nothing special. So it's fine to compile C, C++, Rust without any trouble. If you want something to do something quite naive, it's not going to take you long. It's mostly going to take you some time to implement the runtime, the libc for C. because WebAssembly has nothing for the rest of the world. It's just a language, not an environment. So if you want to compile your language, you generate naive WebAssemblies and you call binarian to handle whatever is specific to WebAssembly. And it does quite a good job at that. So just be naive, it's going to work. So, but if you want to compile Camel or SML or any garbage-collected language, then that's going to be more troublesome because you need to keep tracks of your roots. And keeping tracks of roots, you can either do that into a shadow stack, or you can do some other tricks that are a bit more complex, but you can't inspect WebAssembly stack. It's completely opaque, and for good reasons. So, well, you have to do something, and then there's another problem because your garbage collector is your own garbage collector. If you run inside the browser has a different garbage collector. Pointers between two different garbage collectors is always a problem. And you are not going to be able to collect cycle between the both languages. So, so you want to do something else. In fact, in WASM2, there are external refs that helps a bit with something like that, but yeah, that's not completely the solution. So we want something that is, well, like WebAssembly, quite fast, that does not slow basic WASM code, and can represent any garbage-collected languages. So apparently Camel was kind of a good model. The memory model of Camel was quite a good model because it looks a lot like the actual values of Camel. So thanks, Andreas. That's quite helpful. But there is a bit more because, well, you want to efficiently access values, don't cast too much. So there is kind of a type system for the objects that you can allocate inside WASM-GC. And it's a type system that allows you to go to upcast easily, but don't downcast naturally. But you can still downcast, and you can downcast quite effectively. So upcasts are completely free. They are just even implicit. But upcasts are supposed to be basically pointer equality or something like that. So it's supposed to be quite cheap. And in practice, you can look at that as kind of a structural typing discipline that is encoding into nominal typing if you do whatever you need to describe all your nominal types, all your potential structural types as nominal cases. So, well, where does that fit inside the Camel compiler chain? So that's what the Camel compiler looks like. Not exactly, that's OCaml plus current development branch. So you start from the source, you compile to, you type check, parse, and then you forget the types here, which is basically a non-type lambda calculus. And then you can go to the bytecode, and then to bytecode to JavaScript with JS over Camel. Or there is the old path of the compiler, or somewhat newer path, or the current development path that you will hear about from me. And you can compile to WebAssembly basically from there with WASM-Camel, or maybe from there later, because currently what I'm presenting is kind of a prototype. So why did we choose that level? So basically everything before f lambda is a bit too high level and not very convenient for us, because WASM with GC has functions, has blocks, values, and whatever, but don't have closures. And whatever is before f lambda has explicit as closure in the language. F lambda has explicit closure, so you can separate the construction of function and the construction of the actual closure. And the control flow is quite easy to translate to WebAssembly, which basically allows to build all the kind of control flow you want. It's kind of restricted, the control flows that you can build in WASM, but you can just be naive and let Binarian take care of simplifying that for you. So the next version from the 2 is going to be basically the same thing. There is not going to be any more trouble. So some OCaml. That's the version in F lambda, some kind of printing of that. So if you look at it, you see that we explicitly allocate closures. And yeah, we project from closure. We have explicitly access to fields. So that's quite simple. We have explicit lets everywhere, no nested expression. Something that is quite simple to translate, that generates horrible WebAssembly when you just do that naively. And we do that naively, but we don't care. Binarian is here for us. So everything is represented as what is called an ecref type in WebAssembly. So that's just under any. So any is the level where you can represent any kind of values. Ec is any kind of value on which there is the equal operator, which is quite convenient because there is the physical equality function in OCaml. So we need that level. And we don't need anything that is at the any level but not at the ec level. So quite convenient for us. So why don't we construct anything that is more precise than that? Well, the reason is that the OCaml type system is quite complex. We forget most of it when we go to the Lambda language. It would be quite horrible to be able to reconstruct some interesting type for it. And OCaml programmers tend to be not so nice to the type system sometimes and use the magic function that destroys everything. So, well, we have to assume that the program is kind of well typed, but not too much. So, for the basic values, we use something that is a struct. And for small integers, we use int31ref, which is something that fits into a pointer or standard value in WebAssembly, and which is also compatible to a structure. An int32, int64 are not compatible with those types, but that's something that that fits in any reference. So that's quite convenient, and we kind of pushed for that, and it was apparently not too much rejected. Otherwise, OCaml's arrays are represented as WebAssembly arrays quite naturally. So something about the type representation. Yes, there is obj magic that makes everything troublesome. But also, then when we access a field, we don't exactly know the type, the size of the field we access. We just know that when we access the field n of a value, then it has n plus 1 fields at least, but not much more. So that means that we need to use the subtyping chain that WebAssembly proposes if we want to represent things as struct. And then a block of size n, we could access any field lower than n. But then that means that when we do an access, we take an ecref, we cast to just the size that we want, and if it's the right size, if the type checker didn't complain when the OCaml program was compiled, that should be correct. And the cast is valid. But then we need to have compatibility between different sizes. So the subconstructor, I don't know if we can see, that tells that blocks of size 2 are effectively subtypes of block of size 1. So in fact, it's not exactly that type that we use. We add mutability to every field because, well, OCaml have letrex. You can't build recursive values without mutability, sadly. We have ideas for potential WASM extension to change that, but that's going to be Leo's work to write the details. Also, that encoding is great, but there are stupid OCaml libraries, like OCaml emojis, which has basically one definition for each emoji, and that's a lot. OCaml modules are represented as blocks. And so you can imagine that those are quite long blocks. The problem is that the subtyping chain is quite long, and for good reason, there are limits to the length of subtyping chain, because there need to be something that represent inside the engine some structure of the subtyping chain. And if you have a gigantic subtyping chain, then finding something in that structure is going to take some space, and that's not some space that you want to waste in something like that. Especially that in practice, nobody wants to do something that large. So since we want in WebAssembly that everything has predictable performances, we want the cast to be basically always taking always the same time, having the same sequence of instructions, and not depend on the actual type. So you could encode something that would be logarithmic in the size of the types to actually check. That would be possible, but probably undesirable. And that's something that the user can encode itself. So it's probably a better idea to let the compilers that generate WebAssembly handle itself and do the logarithmic tree of subtyping. But that's not what we do, because basically we're too lazy and we did a naive version. So we did implement the struct1. It blew immediately, basically, because the subtyping chain is of length something like 60 or maybe 100 now. Too small even for standard OCaml standard library modules. So the naive version is just to say, well, everything is an array. And you can store integers in arrays. So you store in href. So it's an array of href with everything shifted by 1, and the tag stored in the first position. It's not wonderful. We could do better, but that's clearly the simplest way to go. But I'm not even sure that it would be slower than the struct version. This has to be benchmarked, and well, before benchmark, you never actually know. And we don't have sufficiently precise benchmark right now to decide. So we might try the other solution at some point for real. So how do we encode closures? So closures are functions and fields that capture the environment. So basically, you just have fields for the function. Because functions are not compatible with the other reference values. You don't want to mix everything in there. So you have to pack them into structure. But it's okay into structure. You can have things that are different types and that are not compatible. And that's all. It works quite well. But if you want to do that, you need to be at an intermediate representation that do actually represent explicit closures. So compiling to that directly from something that is a lambda calculus is going to be a bit troublesome. You want to do the closure conversion before that. So in fact, it's a bit more tricky than that, because OCaml functions and closure have lots of funny things. So that's the actual encoding for the function of type at most 2 arguments, and with closures a function of 2 arguments that contain 1 field. So that one is the function of 1 argument, nothing really special. But we have the recursive definition of type, because WebAssembly allows the recursive definition of types. So the function knows the types of the environment. The environment knows the type of the function of 1 argument. And the thing is that the function of 1 argument in OCaml is the supertype of every function. Because every function in OCaml can be applied to just 1 argument. So, and you don't know really from the type that it's the case. It can be completely dynamic. So you have to be able to cast any function to a function of 1 argument. And so when you apply an actual function of 1 argument, you just call that. But if that's something which has more than 1 argument, then you need to allocate intermediate functions. And well, that's some trouble, but it works quite well. We basically use exactly the same schema, the one that is used for the native OCaml compiler. And that's quite decent. So OCaml have exception. OCaml use a lot of exception. We use that for control flow, for everything. That's nice. And what's also nice is that there is another proposal in WASM that proposed to add exception to WASM. I think that we were not the main target for that originally. We don't have enough weight for something like that. It was C++ that was the main reason for that. We don't care. We are OK to just steal the proposal. So we basically just use that as is. And it basically allows to represent OCaml exception without any trouble. And I think other languages are not going to have problems with that. I've just heard that it's completely going to change soon. So maybe that's not going to be the case anymore. But I trust Andreas and others. That's going to work. Yeah. So it was simple enough. So if it's simpler, then it's really simple. So alongside the actual development, Leo worked on small steps semantic of F lambda and something that is similar to for F lambda 2 to be able to prove things on the compilation. So it's the first semantic of something at that level in OCaml. Well, that's nice. And he has interpreter and stuff for that, and a compiler of the mini version to WASM-GC, just to be able to try his own semantics against some semantic of WASM-GC. We'll see. We don't know exactly the details of that, so there are no proof right now of the actual compilation. We imagine some version, but well, the proof are going to have to evolve. But the proof is going to be probably quite simple, the actual proof, because the semantics of WASM-GC is very similar to the semantics of standard ML, so no problem. So if you want to try that, it's there. So there are 2 URLs for that. You can go see it wherever you want. But that's a prototype. If you really want to do something serious, well, right now it's a bit early. By the way, no actual browser can use that for real, so that must be experimental. So otherwise, that prototype, I think, was basically the first of a kind of real language, because that's just a prototype for WASM-GC. So I think we kind of validated that validated the proposal for something that was not crafted after the fact. Andreas did write a functional language to test the proposal, but he could assume well, he designed it for the proposal. So you never know that if you can patch that into an actual compiler without destroying everything in there. We showed that in 31 ref is quite useful, and that was not obvious at that point that it was going to be kept. But you can't use that for real program right now because we were too lazy to implement the full standard library because, as I said, you don't have libc, so you have to do a lot of things to expose actual useful functions to your program in WebAssembly. So we do compile basically everything in OCaml except objects, but who cares? No, and in fact, it wouldn't be difficult. We just didn't do it. But we didn't do the standard library. We are going to steal the one from Wasm of OCaml, from Jérôme Vouillon. And that will be a lot simpler than actually writing it. And yeah. So how does it perform? Because that's always the question when you have a new backend. So it performs quite well, given that everything is quite experimental. So if you do some classical micro benchmark, which are micro benchmarks, so you shouldn't trust the results. That's basically at worst kind of 2 times slower, and that's basically always the same factor compared to native code. So that's quite good. That basically achieves what was expected of WebAssembly, which is having predictable performances, which is absolutely not the case when you have JS of OCaml. You kind of have the same speed in JS of OCaml in best cases, but the worst cases can be very horrible. But as I said, exceptions were meant for C++, and apparently were not optimized like hell right now in V8. And yeah. But we did hack a few things, just try to avoid the problem. And if we try to don't rely on exception, programs that do rely on exception in OCaml, so Knut Bendix, the preferred benchmark by Xavier Leroy. So usually he says that it performs basically the same as Coq, so it's a good idea to have that fast. Xavier is going to be happy. So it's a bit slower than the programs that don't rely on exception with the exception implementation, because your functions are going to need 2 arguments. You need to check at the return of each function. But that's not horrible. We don't take an horrible slowdown. So either we wait for future proposal, or we push for future proposal on an exception for that to be faster, or we can just use that encoding. So otherwise, should we care about the cast? Probably not that much. We could optimize to remove as much as possible, but that's at most a 10% gain apparently. So V8 has a mod to try to segfault it, where you say casts don't exist. So it's quite cool because you can see the differences between the best case and what you actually have. And you know that right now it's like 10%. We don't really care about that level of difference. We could go a bit lower because fm.2 has more information about types. But well, maybe we won't even do that. So otherwise, what happens when you have to interact with the rest of the world? So we will do what matters for the studlib. But if you want to run on the web, you can also use JS of OCaml FFI, because you can expose the JavaScript FFI as something that would be compatible for WebAssembly and calling the JavaScript through something that is a method call for JavaScript. That's some hackish thing, but that's possible, and that's probably to be quite slow at some point, but possible. Otherwise, you can hack things to get C compiled to WebAssembly and use that. Since that recently there were changes in C-Lang that allows to use the external ref that's still unreleased, but it's probably going to be possible to just compile that, change a bit the header file that you use to compile your OCaml C code, and that's just going to work without too much trouble. Just changing a bit things because the field access is not going to be a null value anymore. And I think I should, yeah. So there are lots of different other options because apparently OCaml guys want to compile. And yeah.
Okay, thank you. If there is one quick question. Okay.
Yeah, first of all, awesome. Great.
No, it's on.
It's on? Ah, okay. Yeah, awesome. I have one question. So with it's unfortunate that the exceptions are so slow in V8 when you use them this way. I was wondering, do you really need to return, though, a flag with every call? Can't you just have a global flag that you set when an exception is thrown and check that?
Is that going to be any better? Because that's kind of going to go into a register compared to a global access.
Might be worth trying. I don't know. I would expect that to have much less overhead. What do you think? Okay. Yeah, just
yeah.
Okay, so let's thanks again.
Oops.
Oh, that's not what it should look like.
Is it mirrored?
Will be in a moment. That looks better. Yes, excellent. Okay, is the mic picking me up? Yes, excellent. Well, thanks everyone for coming to this talk this afternoon about layout polymorphism. So the goal here is to describe an approach that we're working out. This is still all very much work in progress. An approach that we're working out to be able to efficiently compile, to be able to compile code with varying representations into efficient at runtime code. What do I mean by that? So to start wrapping our heads around the problem, we have to think about what is an unboxed type. So that's what I'm going to define in this slide. So if I have a nice type declaration like we see here, and let's say I have P, which is one of these points. Well, the way that this would normally get represented looks like this. So here I'm representing this column on the left could be our call stack. And so we have a bunch of local variables in this stack, and we'll have a local variable P, which will point to a heap allocated object, which will have a little header, that's those 3 dots at the top, as well as slots for X and for Y. An unboxed version of this would look like this. We have our call stack, and even though I have this variable P in my source code, there's actually just room for the X and the Y in the call stack memory. Now, in reality, these would probably just be in registers in the middle of a function, but that's a little harder to represent in a picture here. So this is really what we're talking about. This boxed thing, that's what OCaml has done since the beginning of time. This unboxed thing, that's what Jane Street is doing new and exciting. And so we don't yet have this working. But we are working toward this. So this is our design. Again, this is all sort of work in progress and looking forward to the future. Okay, so with that understanding of boxed versus unboxed, I'm going to make a claim that unboxed types are faster than boxed ones. Right? We have to do less indirection. Right? I don't have to walk to another part of memory to retrieve the fields from my record. I don't have to allocate that memory. I can have better cache locality with unboxed types. But unboxed types are harder to work with than boxed ones. And that's because there's a reason that OCaml uses box types, which is that box types work much better with polymorphism. Right? If in a box type, I know every single value in my OCaml program is going to be represented by one machine word. And that's really nice, and that makes working with the language much easier. So when I have unboxed types, the real reason that they're harder to work with is that they're non-uniform. Right? That x and y that we saw on the previous slide, if I want to pass that to a function, I can't do that the same way that I pass a normal boxed value. I have to pass now 2 registers or 2 slots on the stack. So that means that these unboxed types are non-uniform, which requires different runtime behavior. So I now want to introduce this map example here. This is going to be my running example throughout the rest of the talk. So I might have an array of some type alpha, and I want to map a function over that to create a new array of some type beta. That map function must manipulate values of types alpha and beta. And we can see the little color language that I'm creating here. So green here is for runtime values. Blue is for types. And purple is for layouts. So here, what I'm saying is that to be able to, for this map function to be able to manipulate values of type alpha and beta as it's running, right, we have to manipulate the alpha because we have to pull it out of the array and send it to that function. We have to manipulate the beta because we have to get it back from that function and insert it into an array. So it needs to know, is it represented by 1 register or 2 registers? Is it a floating point number? Is it an int? These aspects of alpha and beta are going to control or have to be apparent in the implementation of map. And that's what I mean by map must know their layouts. I can only compile map after I know the layouts of alpha and beta. So this word layout, that's a new term that Jane Street is introducing into OCaml to describe a memory representation, register convention, sort of these runtime details that are necessary to store values of a given type. If you know kinds in other languages, kind is very similar to layout. In fact, layout is a subset of the space of kinds. OK, so returning to this, here's map. This is the map that we've had since the beginning of time. And so it works over values. But I don't want just value. I don't want just arrays of values. I might have an array of unboxed floats. So here, an unboxed float is going to be one represented by directly by a float instead of by any indirection. And I might want to map over such arrays. So then I have my normal map, and I have this map. Well, and then I realize I actually might have an array of values that I want to map into an array of unboxed floats. So I need to have this one. And then, well, maybe I want to go the other way, and I have my array of unboxed floats, and I want to go into values. And now, actually, it turns out that we're recognizing a need not just for 64-bit floats, but we want also 32-bit floats. This is a real need within Jane Street that has come up. So now we want to be able to do that. But then, of course, we want to go the other way. And we want to go among 32-bit floats. And maybe we want unboxed 64-bit integers instead of 63-bit integers. And this goes on and on and on and on. Right? So in a real implementation of this, we would need all of these maps. I guarantee you everything that's on the screen here, we would have to implement at Jane Street among many, many, many more. So really, we know what the solution here is. We want polymorphism. Right? This is why we have polymorphism, or I should say parametric polymorphism, in a language like OCaml. It's to stop ourselves from needing to be repetitive. It turns out that actually polymorphism is one step too far for what we need over layouts. And so instead, we need layout flexibility. And I'm going to tease apart what that difference is as we go further. But it comes back to polymorphism in the end. OK, so let's look at this map here. So what I'm going to do is I'm now going to say that instead of alpha and beta having layout value, we're going to say that alpha and beta have layout any. So this is what I mean by layout flexibility, is that alpha and beta can have any layout. And it's slightly different than what I might use polymorphism for, which would be introducing layout variables. Getting into a description of that would take us a little bit away from the main part of the talk. If you want to, you can ask questions about that. I'm happy to answer toward the end why we don't need layout variables. But here I want alpha and beta to have any layout. Well, what is this any layout? It is a sort of super layout of all possible layouts. And so when I say that alpha can have any layout or beta can have any layout, it means that in that type of map, that alpha can be a value type, that these are all of the normal types that we've known in OCaml, but it can also be an unboxed float 64 or unboxed float 32. It can be an unboxed int 64. It can be one of these unboxed points that we saw toward the beginning, which is going to be a sort of a product layout. And so by annotating alpha and beta with any of those types of any of these layouts or any other that we can imagine can be substituted in to alpha and beta. So layout polymorphism, allowing actual layout variables instead of this colon anything, that would be fine. But layout flexibility is simpler, so we're going to stick with layout flexibility. This is in contrast to Haskell, for example, which does have full polymorphism here and allows you to have what are equivalent to layout variables. OK, so then the next question is, so here I have my nice type of map that's going to subsume all of those map types that we saw a few slides ago. So that's great. But how are we going to compile this to efficient code? I said earlier that we can't do that. And indeed, we can't. So we could compile this to inefficient code, right? I could preserve the layouts as little tokens at runtime, and then call the map function and look at the tokens and say, oh, once I know the layouts, then I know what registers to access the next arguments in, or I know how to represent this stuff in memory. That's going to be really slow because it requires extra branches at the beginning of every single map. We don't want to do that. So efficient is carrying something here, right? We could do the inefficient thing really easily. But we can't do it efficiently. So what are we going to do? Well, we're going to do layout monomorphization. Right? This isn't a huge surprise. It's what other languages do. And I should say right now that there's no huge twists and turns that I'm going to take in this talk. But building all these pieces together, requires some delicate care. So layout monomorphization. What I mean by that is that this map that works over any layout, I'm just going to stamp out copies of that at every layout that I actually need. And that's the basic idea. But of course, nothing is quite so simple. So there's some details to walk through. So one question is that given that map, exactly how am I going to monomorphize it? So here again is the type of my layout flexible map. The first step to be able to understand how the layouts flow through the implementation is I'm actually going to translate this layout flexible map into the full layout polymorphic one. So this is using some hypothetical syntax that we don't expect to introduce into Surface OCaml. Unlike this actually already we can type that in and parse it and make sense of it in our branch of the compiler. But down here, this is this sort of hypothetical syntax that I don't think we'll ever implement, where we have layout variables y1 and y2, and once we have those, then in the implementation map, we can easily sort of trace how the layout of this variable flows into some other function, right? Maybe map itself calls another layout flexible function that we'll need to monomorphize, and we need to know which monomorphic instantiation we would need of that function. And so the first step is to use sort of proper layout polymorphism. Then, once we've done that, now we can just monomorphize the thing. And so if we have a usage site that instantiates this map to work over an unboxed float and say a string, which is one example of a value, then we would monomorphize the layout flexible float, which has been translated to a layout flexible map, which has been translated to a layout polymorphic map into this monomorphic one. Although, to be clear, this is still not monomorphic, right? There's still type variables alpha and beta here. Right? We're not doing full monomorphization. We're just doing layout monomorphization. And then, once we've done that, we can compile that. So we don't need to know the types to be able to do this. We just need to know the layouts. That's the information that we need to be able to manipulate these things at runtime. In a sense, that's almost the definition of what layout is. It's the stuff that you need to compile something. And actually, as I've discovered in other work, that depending on your compilation strategy, exactly the definition of layout might change. Okay, so then the next question that we have to ask is, so if we're going to do this monomorphization, that means we need to go and find the code to monomorphize. So here, I have somewhere else in my program, I have a call to map that looks like this. So I'm calling map, and here is some function f of this particular type working over some array. Well, to be able to monomorphize map, I need to go out and find the code for map. But the problem is that finding that code is going to depend on my module m. And module m is a runtime value. I don't know necessarily where it's come from here. Maybe it's a first-class module. Maybe I'm in the middle of a functor, and m is bound as a functor parameter, right? In these cases, among a number of others, we can't really know exactly where the code for m.map is. And so then we can't monomorphize it. We need to know where this code is at compile time to be able to do that monomorphization.
But sometimes you do.
Sometimes we do. And we will when we have a static mode. So this is, I'm using the word mode as in sort of modal type theory. It fits into that same structure that you may have seen in our blog post series about oxidizing OCaml to track data race freedom. But another mode in that space is going to be the static mode. And these are for expressions which we can reduce to a value at compile time. And so we want m in that m.map. Actually, we want all of m.map to be type checked in the static mode, and then we'll be able to find it at compile time. So some things can happen statically, like substitution. So this allows us to do some functor applications. We'll see a counterexample on the next slide. But in a functor application, you can just think of that as beta reduction, which is mostly just substitution. We can figure out how to do that statically. On the other hand, we can't do side effects statically. So some operations we're not going to be able to do. There's not really too many twists and turns also in this design. If you look on the ML Workshop program, there's a media attached on this talk, and you can find the typing rules there. There's a sort of a write-up of the abstract that I submitted for this talk, and it has a bunch of preliminary typing rules. Again, we haven't implemented it, still work in progress. But one challenge around this is that sometimes it looks like we're going to want to perform side effects at compile time, and that's bad. So here's an example. So if I have this functor here f, and maybe f defines functions f1 and f2, and then map, the thing I might want to use somewhere else, depends on flipping a coin, right? This would be a bad implementation of map, but it's something that you could type in. Running this functor is actually, in an OCaml program, is a runtime thing that will flip the coin at runtime at the place where you instantiate the functor, and it will choose either f1 or f2. We don't want to do that at compile time for many reasons. And so the way that this would work is we can't have compile time side effects. That's bad. And so instead, the current plan is to take the functor f. If you try to apply f to some argument and then call map in the static mode, then we would sort of look at this, figure out that it's no good, and then reject. We might imagine something more glorious where we do some kind of purity analysis and say that the type of this functor is an impure functor which doesn't work in the static mode. We could imagine all of that. I think much easier would be, let's just try it and see if it wants to do any side effects. Because all of this is at compile time anyway. So instead of coming up with a glorious kind system, we can just sort of try the thing and then fail if it doesn't work. In any case, we definitely want to reject an application of f in the static mode, even if we know f statically and even if we know f's argument statically. We don't know the application of f to x. OK, so that's the static mode. That's sort of the more intellectual beating heart of all of this. But throwing up a bunch of typing rules, all of which is kind of easy on its own, is not a good use of time. So we're going to move on to the next challenge, which is separate compilation. So the monomorphizations are driven by usage sites, right? And so I might compile map in one file over here, and then use map in some file over there, and then I want to go back and figure out what the monomorphizations are. So how are we actually going to do that? So one approach that we're thinking about is to use the build system. So when I say the build system, if you want to, you can imagine Dune, which is the build system, well, roughly the build system that Jane Street uses. But it turns out that that's not, that's not a requirement. You could do this with other build systems also. But I'll demonstrate the details of this on the next slide. One other possibility, I've said possible here because we're not sure what's best. The other possibility is to use C++ style deduplication. So maybe every time we need a monomorphization of map, we just do it in that particular file where we need the monomorphization. We'll end up with many of the same monomorphizations, and we'll just deduplicate later. It's unclear which will be better. But I kind of am excited about this build system approach. So what do I mean by that? So here I have a usage of map, and now we're going to make a simplifying assumption that this particular m here, that's just m.ml. Right? There was not a functor application. There's no first-class modules here. We're just plucking from m.ml. And in fact, I'm also making a simplifying assumption that map is just defined as a lambda right in that module, that it's not sort of doing some other kind of indirection. So given that, then when I see this usage site somewhere, all we're going to say is that, oh, well, that usage site, to compile that, I need to be able to call this mmap float64 value, right? Where here, float64 is the layout of float hash, and value is the layout of string. Ooh, I realized I should have colored that in blue. I apologize. Or to be clear, I should have colored this in blue. These are types, but this is just the name of a function, right? And so I've taken the module name and the function name and the layout to sort of build this mangled name. And when I'm compiling, say this is in u.ml, usage site. When I'm compiling u.ml, we'll just record that before linking, I need to have this function somewhere. But as I'm building u.ml, I can just call that function in my .o file, and everything will be fine because I don't only have to execute it after linking. And then the build system just it records this dependency and then knows, oh, to get that function, we just have to do an operation on m.cmo, right? We could work out sort of all the details. I could write like makefile style rules for it or something. It's not all that exciting. What it does do, though, is it does require that the build system be able to deal with these dynamically generated dependencies somewhat late in the process. So that might pose to be a challenge, and that challenge might be big enough that it's better to just do the C++ style deduplication. I don't know. So we have these multiple possibilities. So it's worth pausing for a moment before I wrap up, just to consider what happens in other systems. So one other approach to this would be to do sort of more aggressive monomorphization in something like Milton, right? So Milton does whole program compilation. It gets to see everything all at once. That approach is not feasible for Jane Street. We have 40 million lines of OCaml code, and we're not going to slurp all of that in all at the same time. C++ has support for this through its template mechanism, but C++ has no notion of abstraction for its templates, right? The C++ template must be written in a header file. You must always have it as you're compiling. There's no notion of separate compilation or abstraction. And it has to do this lingered deduplication. Rust has full monomorphization, but it still maintains separate compilation and takes a different approach than Milton. But it doesn't require the static mode because we're not going to store polymorphic values inside of structures the same way that OCaml does. And so the problem is somewhat simpler in the Rust context. For C, Java, and Haskell, it's kind of fun to be able to lump those languages together. It's not often that those three end up in the same bucket. But there's not really support for this idea. You just have to repeat the code. I suppose in C and Haskell, you could do some C preprocessor stuff, which goes fairly far, actually, for this. But maybe not the most beautiful solution. So Haskell has support for this kind of thing in its type system, but if you actually want runtime code that works at multiple layouts, you need to just repeat your code. C# takes a very different approach, one that I haven't really touched on before in this talk, which is it does runtime code generation. So that's another possibility, is we could get to the point that we need to do the sort of layout unknown thing, and instead of making a branch at that point, just say, oh, at runtime we need this specialization, and it just creates it right there at runtime. That requires lots more technology than we're going to develop just for this. So this sort of fits into that space. The static mode is probably the biggest part of this that's really something new on top of what we already have. So I'm going to make a sort of a shameless plug here. If you want to work on this, we have just opened up a sort of pre-faculty / postdoc position where you could come to Jane Street for a year or two and work on this and other sort of bleeding edge research questions. So there's more information behind that link there. And that's all I've got. There's the link still. Thanks very much.
So one obvious design possibility didn't. Okay. One obvious possibility that you didn't explicitly mention is that at the declaration site of map, you could just say to the program, please write out all the instances you like. So they don't have to duplicate the code, but they have to write the signatures, and then all of those are available. And that's very simple compared to messing with the build system and Dune and who knows what kind of thing. So it might be a good jumping off point.
Yes, and actually we were planning on doing that as sort of an earlier stage of this. One challenge is that because we can take a type like point that anyone can define anywhere and then use it unboxedly, it's going to be hard for the author of the function to be able to anticipate all the monomorphizations that will be necessary. So you might end up in a scenario where there's got to be some way later on down the pipeline to say, add these monomorphizations, and then you sort of do it explicitly. But it's not just so simple as being able to declare it up top.
So, is that working? Yeah. Okay. Is there a assumption? I mean, I'm curious how this interacts with the sort of nested polymorphism, which I understand OCaml has. So in other words, if you're just having regular polymorphic functions, right, you have pre-nix form, and so you can deal with the layouts at the application site. But if you had a polymorphic argument which had layout flexibility in it, the point at which that function gets defined, I mean, the second,
Yeah,
I think you understand.
I do. So I can think of sort of two different answers. So one is like in normal functions, so Leo gave a talk this morning about having polymorphic parameters. We're not going to allow layout polymorphism in that spot. We can just sort of statically rule that, like syntactically, essentially. We just can't do that. But the other place that it could happen is in a functor parameter. And so in that scenario, it's this static mode check. We won't be able to know what the function is, and so we can reject that at compile time, just saying, there's no way to do sort of layout monomorphization in this context.
Okay, so yeah, let's go. At some point, you're going to have to make the two pieces of data that have different layouts interact with.
So to cast from the casting from what to what? I'm not sure I understand. So just to repeat the question, because the mic wasn't working. So the the question is, how do you cast sort of from one layout to another? And it essentially depends on exactly what you want to do. So in the case that you mentioned, going back and forth between, say, box float and unbox float, there's just going to be a box function and an unbox function. So the sort of the root set of layouts is fixed. So like the compiler sort of says, okay, these are the set of layouts, and then you can make products and sums out of those layouts. But as we do that, we just sort of build in the conversions. Sure.
Okay. Yeah, that's great. I never thought I'd hear the words. I'm excited about the build system being uttered here in this workshop. But my question is, why is deduplication important? You should map, which is a small function, which conceivably wouldn't be a huge problem if it was duplicated. Do you really have big functions that are layout polymorphic whose duplication would actually be an issue?
I mean, that's a great question. I don't really have an answer yet because it's still sort of too early. My guess is yes. Yeah,
Okay.
In my short time at Jane Street, if it is possible, it happens. When you have that much code, we'll build it out.
Cool, thank you.
Oh, okay. Ron can maybe give a concrete example.
Just a super concrete example.
No, not.
Just a super concrete example. You might want to parameterize a bunch of trading logic over the representation of price. And that representation of price might have multiple different layouts. So you could have, 500,000 lines of code that's layout polymorphic, and that might be instantiated at multiple different things, and you might want to have that like multiple versions of that alive in the same program. So like this totally can happen.
Okay. So what about data representations in data structures? So Milton, for instance, is doing a lot to optimize data layouts in records and so on. So once you have trees, for instance, you might have unboxed floats inside those trees, right? Instead
Yes.
of having.
So I'm not sure I understand the question. I mean, yes, we want to have that.
Well, does this tooling you're doing also lead to efficiencies in types? You didn't mention anything about type specialization.
Oh, yes. I mean, I don't think we would need type specialization even for that. I mean, I wanted to focus more on the sort of the layout polymorphism part than the unboxed type design part. But we will allow you to sort of, if you're writing a structure, you can use an unboxed version of another record, say, so like that point record that we saw at the beginning. If you just put a hash at the end of that, point hash will just get inlined into some larger structure. So obviously you wouldn't want to do that recursively because then you'd get something infinitely large. But if you want to have a rich structure at compile time but have it all flat at runtime, that works just fine.
Okay, so that's the end of the session. Thanks, the speaker again. Oh, that's the break. In about 30 minutes.
Yes. This is still live. I don't know how to turn it off. Thank you very much. Thanks.
the two. And Pierre would.
Okay, can you hear me?
Speak again.
Yep, perfect. So sorry, it's me again. So static analysis in OCaml, but not for verification. So f lambda 2, as I mentioned earlier, is an intermediate representation inside OCaml. So, and that's a path where we do static analysis to know some things about the code to optimize it. So that's a work that we do at OCaml Pro with GenStreet, and mainly, well, Marcinwell and Leo, but many others. So why are we making f lambda 2? Well, because we can, and because there were limitations in the previous versions. And I won't go too much into detail because there is a talk tomorrow about that. But here I'm going to describe how we accumulate, manipulate, and find informations about the code for the f lambda 2 simplifier to make it know things about the code itself. So the constraint, which is not simpler for a static analyzer in general, is that the code is modified at the same time as it's being analyzed, which is not the kind of thing you see in verification, and makes it could make everything more difficult. But since we have that constraint, we implement everything in a pure way, and then that's quite okay. So it started as kind of an ad hoc analysis, and it evolved. We called that a type system at some point. In fact, it's really an abstract interpretation, so, well, now we call it that way. So the simplifier is something that traverses the code, accumulates information, and then reconstructs the code with differently to make the code better. So what do the analysis expose to the simplifier is quite simple. We have creation and deserialization of an environment. So environment is the abstract domain. And then we have updating function to add information in it. And basically, we just add properties. Then we can meet as an abstract meet, or join when we have different branches going to the same point. And then we can clean it. So that's for updating. And then for looking at it, well, meet is for updating, but is also a way to query the domain. Because basically, you can meet a property with the current domain. And if it's bottom, then that property doesn't hold. So that's the basic function that we need. In fact, usually it's not fast enough just to meet. So we have faster versions that are less precise, but are quite useful often. Because, well, we need to compile GenStreet code base, and if we're not fast enough, with 40 million lines of code, apparently. So the difference between verification and compilation for an abstract domain. So from high level, not that much. We have an abstract domain. We need to accumulate data on it. But the main difference is what we expect in terms of precision into the domain. Basically, we often need to be faster than the verification domain. And so that's one constraint. But on the other hand, if we are bad, it's not that problematic. In a verification domain, if you have something that is top, then you don't know anything. You just know that your program don't verify your assertion, or verify your assertion, but you don't know anything. In our case, it's just a bit slower, maybe just in a local case that don't matter that much. So we can basically just don't consider part of the language that are not going to be amenable to optimization and concentrate on the parts that might be a lot simpler, where you can do optimizations that matter. But on the other hand, if we have information loss, the generated assembly is going to be different. But you need to look at the generated assembly in some way to know that your domain is not precise enough, or to the intermediate phases, but the user usually is not going to notice it. So, what are the kind of properties that a compiler needs to know about values? What is useful? So, the basic properties that we want are numerical constant in general, because that the domain is going to be used for constant folding. So anything that is constant is easy to track, and we are going to track it. But we want a bit more. So we have some information about the numerical constant, but also about blocks, to simplify access to blocks and to basically avoid access to blocks when it's possible, and to remove allocation of blocks, because allocation are quite expensive. Well, not directly expensive, but when you accumulate a lot of allocations, that's expensive. And if you can remove it, well, that's good in general. So we want to simplify function, but also we need to find functions. If you don't know what is a function and which function it is, you're not going to be able to specialize function calls as direct calls, and you're not going to be able to inline. And specializing to direct calls is very important because indirect calls are quite expensive by default. And, well, if you know things about variants, then usually you're going to be able to detect some dead code, dead branches in if, and that's a good idea to remove it. And with a few more information, you can know things about values precisely, and you can do some kind of unboxing where you don't need the user to tell you about the value to be able to unbox some things. So what does the domain look like? So the values in the domain are for numerical values, just small finite set, simple. It's mostly simple, but because that's most of the time that's sufficient for optimization, and we don't need that much more. So blocks are kind of the most important structure where we need to be a bit precise. So we only track precise information about immutable blocks because that's simpler. And the OCaml memory model in general would make it quite harder to be able to do a local analysis that says anything about mutable values. And then we track the size of blocks with the contents, and yeah. And closure, we need to know which closure it is and the contents of the field. So basically, it's the same structure as blocks. Yes, and relational information about everything. So blocks, what I described is kind of a shaped domain. It's a very simple shaped domain, but it's a shaped domain, where we have two kinds of shapes that can represent block. They are complete shapes that usually arise when you allocate a block or when you take information from the type checker, where you know that a block has a specific size, can have a specific tag, and maybe things about what is inside the block. But when you do a get field, access a field in a block, you only know some partial information just about that field. And the size of the block is bounded by the field, but you don't know much more. And of course, we can do between both. So functions, function basically the representation is just the code of the function. When we can actually inline it. When they are too big, we just drop the information. But we can also capture some information about the semantic of the function. Sometimes that's useful. So closure, as I said, they are like blocks. They contain functions in some kind of indices, fields in other kind of indices. They are kind of the same thing as the integers you use to access a block, but just for convenience, they are not integers because when you want to remove them, you don't want to renumber the fields. So, if you have just a naive domain just describing that, which basically is the case of the old version of the compiler, you can do quite a lot of things already, but you're missing some information. And you're not going to be able to track the information about one of the most important kind of values in OCaml, which are variants, the type definition of different cases. So to be able to represent that and have information in that, you need some kind of unions. And unions, if you don't do that in a smart way, in an abstract domain, that can be quite expensive, that can blow up quite quickly. So we restrict our unions just to some specific cases where we can discriminate quite quickly between the case of the union. So those types, it's okay, we have a union to represent that. But something that arises basically from a JDT, you can produce a case like that without a JDT, where you want to do a union between an integer and a string. We are not going to care about that. It doesn't happen often enough in a situation where it matters for optimization to be able to represent precisely that. And the cost to be able to analyze that compared to the benefit doesn't justify it. So it's going just to be top. So as I said, we have relational information, which are mainly aliases that are useful to track the relation between variables and fields of stuff or other variables. So if you look at that example, we have two variables arguments to the function. We produce a block which contains that, and we extract the fields of that block. That's easy to optimize into something like that, because we could find that the alias that x is the first field of block, y is the second field. We can remove the access to the block. Then by removing the access to the block, we don't need the block anymore. We can remove the allocation. Can just do that. There are more complex cases where if you have relational information, you can also discriminate branches. Here, the block has twice the same field, so we can know statically that the last case of the match is unreachable when we do a meet on that case. I'm not sure that matters that much, but since we have that anyway, well, we can represent that. So to be able to track something like that, we have an aliasing domain. And that domain is a must alias domain. We say when two variables are the same, but that doesn't say anything about may alias or must not alias. Basically, usually may alias is important to optimize mutable code, to say that when you mutate something, it's not going to mutate something else. We don't care that much about mutable code, so, well, we don't care about may alias in general. So to store all those things, we store them in an environment that we propagate through everywhere through the code. So basically, an environment is a map of variables to an abstraction, an approximation. And we can do meet on given an environment and types. We can meet the types under that environment and enrich the environment with some new properties. So imagine that kind of code. If we propagate the environment through this, you will see that at the beginning, we start by knowing not that much, but since it's OCaml, we can find some information about the type of X. So X here would be alpha pair, and that couple. And in that if we know that, we can produce an approximation that says that x is something at the beginning of the analysis of the function. Then when we bind the y variable, that y variable, we are going to extract it from the x. So we are going to remember the alias that it is something related to the first field of x. Then in the first branch of the match, we want to know in some way that it's related to the first field of x. We discovered that y was a. Then we want to be able to find that first field of x is the same thing as a. And to be able to do something like that, the basic way to describe it is to have a reduced product in, between the value domain and the alias domain. So a reduced product is kind of, you have two different domains, and you want that we implement independently, and you want to make them communicate. And when you do a meet or something like that, you try to propagate every information from one domain to the other. So in general, implementing reduced products are quite expensive or even sometimes impossible. So we don't do exactly that. We do an approximation of the reduced product in a strange way that we will see a bit later. That is quite more efficient. So the most important operation that we can do on our domain is the meet, which is used to query the domain and introduce values in the domain. So meet happens below an environment, and have two types that we meet in that environment. So to speak about that, introduce a few notations. So the types are the things that we are able to represent. So the naive things, top, bottom, not very interesting. So we can also have things that say this type is an alias to the variable x. That's closures. We won't say much about it. And that's the blocks, where we can put in unions. So we have different cases where it can be blocks or integers, or the top of integer. Not very interesting. And with blocks, you will notice we have some things that are extensions that we will speak about later. And close to that, we have the environment, which is a set of bindings to types and set of aliases, which are unions of variables that are supposed to be the same. So the code is that environment I represented as yellow in the slides. So the interface of the meet, as I said, so it's the environment, two types, the meet, and then we have a result type and a result environment. A naive meet is any environment you meet two types that are incompatible. So a block of type A, but we don't know the contents, type B, then it's bottom because, well, that's incompatible. But if you have a union and you meet two things that are incompatible and things that are compatible, then you keep just the compatible part. It's a pointwise union. You meet every part independently, but in practice, since all the things that you can actually represent in the union are always distinct, it's quite efficient to do that union in general. Here, we can also meet known tags to blocks where we don't know the tag, but we know the content. Then you know the tag and the content. And that's to show that the meet, when you implement it, it has to be in some way a fixed point, where you discover that two things have basically the same shape. Then you can, like a type checker, say that you push the constraint below, and you have to check below. Well, top and something is going to be the something. When you have aliases, the meet is a bit more complex. It's not just values. So if you have an environment where you don't know anything about x in the beginning, you meet a type that says it is an alias to x, then you're going to discover that X in the environment is that new information, quite easy. But sometimes there was something that you knew about X, then you have to push the meat inside the environment and continue that. And that one is to demonstrate when you have something a bit more complex, you meet aliases between them, then you have to propagate that a bit further in the alias domain. Here you have two representations of the type, you meet the aliases, then you have to find fetch in the environment the actual concrete representation of those types and say that you create a new meet between them, and you should choose one variable to be the canonical one. So here y becomes the canonical alias for the set xy. So we return y now, and you say that x is equal to y there. So now whenever we look at x or y, we will know the same information about those types. Yeah, I will skip about that. It would be. So if we, too much details. So environment extensions. So we have something that is a bit complex that we can store inside blocks or alongside functions, which are basically small sets of environments that we attach to a domain of a value. That is quite useful to describe complex structures. So when you have a function, for instance, we can store some basic summary of its semantics as an extension. So basically, that function returns a pair of things that are aliases to its arguments. So we say that we can say that in the type. So extensions can be attached to anything that can be part of a union. So for instance, we can encode the isInt or getTag primitive in the compiler as an extension. And that's quite useful because that allows us to discover things about the value related to the value of a Boolean. So the isInt primitive is something that isInt of x tells you whether x is an integer or not. So you just create the value when you evaluate the primitive. You store the union in the environment. And then when you do an if of that Boolean, in the two branches, you are going to know that in one branch, it's a 0 value, the false, and the other one, it's the true value. And you will discover, alongside that if you have only one case of the extension, then you can put every information from that inside the environment and then rediscover things about a different value. So that's the example which I said, where we discover here that when we do that meet, we remove part of the type, and when we remove part of the type, then we have the right to propagate the extension there and rediscover that that is more precise. So that's quite useful because that allows to destruct the blocks as the actual block and properties about the block, and don't implement inside the compiler a match on the block, but only match on single integers, and that limits the size of the intermediate language. So that kind of extension is quite powerful. We can encode things that says a lot of things about values. So for instance, that's not obvious, but if you have that in your environment, that's equivalent to bottom. But to be able to discover that, we need to test all the cases independently. And that's going to be expensive. If you do that in general, that's going to be NPR'd. And you don't want something NPR'd in your compiler. So basically, we don't try to look at the content of extension before actually having a single case in our unions. The other side, so we had the meet. We need the join to be able to produce things outside of merging branch. So when you have a if at the result of the if, you need to put something that is a join. So meet what's on types. Join is an environment. Since the environment basically represents the flow of information inside the program, you have that represents the flow of values, and you have to join the environment. So the join, quite simple. If you join things that are different, then you join the thing independently. But if you join things that are related, then we push the join below. So that's some place where we lose precision. But well, if you want to do some abstract interpretation, at some point you're going to lose precision sometime. So join of aliases is another place where we might lose precision sometimes. If you join aliases where you have values linked to those variables, then the result of the join is something that is going to represent the join of the values. You don't know anything anymore about the aliases anymore. But you can still know things about the aliases if you join variables that are supposed to be aliased in the original environment. So those were examples of join on the types. And joins on the type are useful to implement the join of the environment. So to join environment, basically you have to find every constraint in both environments and join them independently. So that's quite expensive if you do that naively. And you don't want to do that naively because environment can be quite large when the code is quite large. So to improve that, we try to find the smallest part that is actually different between the two environments, and then we join just that and we meet that to the rest. Just to say, you might be surprised, but we don't have fixed pointer widening because we don't need. And yeah, conclusion. Yeah, that's in production at Gen Street. Apparently they are happy, and you can try that if you want. And yeah, if you want to do that for UML, I think that's going to be compatible. In general, there's basically nothing specific to OCaml. Because we don't have fixed points. No, but why don't we need fixed points? We could need them. It would be too expensive to do that properly. And our domain would be really hard to check for inclusion. It's quite difficult. We could have some tricks to find a post-fixed point and find stuff, but not that easy. But it would basically be too expensive, and we want to find properties about the values. So there are things for which fixed point is useful for us, and we have something separate that do fixed point on specific properties that are quite easier to do than an abstract domain. And we use the result of that to inject back as specific aliases for the abstract domain.
Just to confirm, I mean, you're planning to put it in F lambda when it's implemented, or it's already? What's the status of?
It's already in F lambda 2, which is in production at Gen Street. If you want to try that, it's in the OCaml F lambda repository.
Oh, okay. So it's kind of, so it's already implemented. It's not in the main line, but it's already, so
yeah.
You have the experience of. Okay, great. Any more questions? Okay, let's thank the speaker again. Okay, so the next, the last actually talk of the session is again about abstract interpretation. It's design and implementation of abstract interpreter for camel program. A preliminary report on the Salto analyzer. And Benoit Montague would present.
Okay, I guess you can hear me. Okay, so let's start. So yeah, this is about the abstract interpretation of OCaml programs. This is very much work in progress. So please be tolerant about the current state of the affairs. So this project is developed at INRIA Rennes, and there are several people working on this, Pierre Lermusio, Thomas Genet, Thomas Jensen, and I would like to thank Pierre Lermusio, who really gave a great boost to the project when he joined it. And this is funded by INRIA and Nomadic Labs, who is a company that develops the Tezos blockchain. And all this story really started when I discussed with Nomadic Labs engineers, because they were a bit concerned about their code, because they have a large piece of code that changes quite quickly and that they have to release on a regular basis. And although they're very serious about code reviews and testing, well, they are keen on having greater guarantees about what they release. So especially exceptions, because they can make your program stop really abruptly. So this is a very humble attempt at a recurrent problem in the ML community, which is trying to detect unquote exceptions. So the Salto project is about mainly detecting unquote exceptions, and these can arise in many cases. So a user can provide assertions. You can just forget about handling division by zero, of course, but any access to arrays or strings also checks for bounds, and these can raise exceptions. You also have in OCaml this polymorphic comparison that may raise exceptions when it's recursively calls at some point on functions. Seasoned programmers sometimes use unsafe functions to get to squeeze more performance, and you would like obviously to also have the guarantee that they are called on arguments that are okay for these functions. The long-term goals of this project is to support as much as OCaml as we can, but that's many features to support. In particular, algebraic effects won't be easy to analyze, I think. I would also like to be able to detect some parts of the OCaml semantics that are explicitly not defined, because it makes the life of the developers of the OCaml compiler easier. And one of them is the order of evaluation. Okay, so as a midterm goal, I would also like to detect whether a program depends or might depend on this order of evaluation. And I'm sorry to disappoint many people in this room, but this is really a way longer term goal to support concurrency and parallelism that was recently introduced in OCaml 5, and also to support the parts of the standard library that rely on how the data are actually represented in memory that is gathered in the OPJ module. Okay, so today I'm going to talk about mainly the first part. So it's a long-standing, this problem has been studied many times in the ML community. If you're not familiar with this, you can split the related work in two big families, type and effect systems on one part. And these are great because they are modular analysis and have fairly good performance, but the precision is not so great, especially when you have to deal with user-provided assertions. So one of the main related works in that area is the work of Leroy and Pessot. And the other half of the related work is mainly extensions of control flow analysis. Okay, so these are whole program analysis that are not modular, slightly more costly, but they have the ability to get more precision, especially when you have to analyze user-provided assertions. And maybe the work that is closest to what we've done so far is the work from Yi from the 90s that also developed a static analyzer, an abstract interpreter for standard ML. Okay. So the principle of this analyzer is, this should be no surprise to most of you, given any sub-expression of a program, call it E, try to find out an overall approximation of the values that it might evaluate to. And also, in case this evaluation might raise an exception, try to find out an overall approximation of the sets of exceptions that might be raised, and also an approximation of in which call stack it might have been raised. Okay, and actually we are going to analyze only expressions that we are sure will not be unreachable. Okay, so that means that presumably only the functions that will be actually called in your program will be analyzed. Okay, if you have a library but never call any function, that's easy. The behavior is just you just create a bunch of closures, no exception will be raised. Okay, and we base this work on a former work of ours that we published at PLDI a few years ago that was dealing with the abstract interpretation of the pure lambda calculus. Okay, so the main novelty that I'm going to talk in this talk is an abstract domain that represents sets of values that are defined recursively, and also another fact about the implementation, which is the use of what we call a dynamic fixed point solver. Okay, so what we have achieved so far is we have an abstract interpreter that runs. And so we support higher order programs, mutual recursive functions, a fairly large subset of the OCaml language. So algebraic values, deep, but not only shallow, but very deep pattern matching is supported. It's not written there, but gathers are also supported. Of course, we handle exceptions. Modulars and functors are supported. That was a big amount of work. But so far, we are not able to analyze programs that perform mutable changes or mutable data structures. We are not able to support laziness objects, and I told you already, OCaml 5 features. Okay, so what is interesting is that the whole analyzer is a big functor that is parameterized over the domain of values that it uses. So it's easy to change this domain and make experiments. And it is a forward analysis, okay? So it means that it's not guided by which assertions are written by the programmer. Okay, for each step of the program, it tries to do its best to find the most precise information it gets. It is context and flow sensitive, and contrarily to F lambda 2, we are not trying to infer any relational information so far, just because we haven't found enough time to do it yet. Okay, and I propose to have a quick demo. How does it work? Is it big enough? Okay. So here have written down, have copied the type of the list that you all know, of course. This is not important and should be removed. Up. And I have rewritten the for all function that tests whether a property holds for every element of a list. Also have written down the filter function that only keeps elements of a list that satisfy some property. Okay, and I basically built a list that may contain some integers. Then I filter out the results so that I keep only these elements that are above 17. And then I write this assertion that, well, the list should only hold integers that are above 17. So the analyzer should tell me that no assertion is raised, right? So here I have the analysis results. You can see that, yeah, apparently no exception was detected. And I'm not lying to you, because here if I assert instead that every element of the list should be strictly above 17, and then if I analyze again, then this time I will get the fact that, well, assert failure might be raised. Okay, so that's an easy example. I have maybe another one that is more interesting. It's a bit longer, and the analysis takes 30 seconds or so. So let me start it right away. And so it's basically a copy of a part of the map functor that you have in the standard library. That's interesting code because you see there's a lot of exceptions that might be raised. It depends on internal invariance of this data structure. And what is even also interesting is the fact that the user code that calls, let's say, the merge function, so it provides a function as argument that has this interesting case where we basically all write this down when you use the merge function, that if the function is given the non values, then this code should never be called on that case. So you see I could have written assert false, but I have written raise impossible instead. And I hope that, well, the analyzer will tell me that indeed impossible is never raised. And let's have a look. Yes, it has finished. Let's have a look. So what are the alerts? Okay, so invalid arguments might have been called. If you look at the results, please trust me, it's only the rebalancing function that raises this invalid argument exception. And if you look at the rest of the code, what do we have? Do we have any other alarm? Yes, okay. We have one internal assertions that it was not able to prove could not happen. Okay, but what is really important from my side is that this raise impossible is showed to never happen. Okay, and that's not easy to obtain as a result. So how does it work? So we basically have this. So this is a simplified version of the domain of that represents the sets of values. Okay, so it has different cases. Okay, so it's a big record that says it's either these possible values that are integers that are represented by an abstract domain of integers that you can choose, or it's a bunch of variants. So these constructors given to arguments represented by the same domain, or pairs of the same things, or these possible functions with this closure environment or top. Okay, but if you have only this, you cannot represent interesting information about, say, lists, because you only have you can only represent a list of size up to some depth. Okay, so here, basically, I added I added a variable and a constructor that says that, well, this is a recursive definition. So basically, if you're familiar with equirecursive types, this is the same idea. The thing is, this operator new, by default, is never there, but it is introduced by the widening operator, which is an operator that is essential in abstract interpretation that somehow generalizes the results so that you get so that you find some fixed points. Okay, so really all the cleverness of the abstract domain relies in this widening operator, and I won't have time to tell you about. So of course you can represent using this the piano numbers, but you can also represent a set of closures that are the continuations that would be passed to a CPS version of the factorial function. Okay, so the continuation of the CPS version of factorial is the continuation might be either the identity function, it is the final call of the CPS, or it's going to be take the result, multiply it by n, which must be an integer greater than 1, and then pass it to the continuation, where this continuation is, again, well, the same thing. Okay, so this is the kind of abstract values that the analyzer is able to infer automatically. So, as I told you already, the main ID should be familiar to you if you know equirecursive types and union types, because these sets of values can represent sets of values that are not well-typed. Okay, so I can say it's either an integer or a pair of values, for instance. But the ID it was already present in the 90s when Hentenrich and Le Charlier analyzed product programs. Okay, and if you are familiar with tree grammars or tree automata, well, you can see this also as a subset of these well-known devices to represent sets of trees. And what is interesting is that so you can see these abstract values in two ways, either as graphs, so taking the tree automata point of view, and for them you have efficient algorithm to compute different operations on them that are necessary to define an abstract interpreter. Or you can view them as terms with bound variables. The alphas are these bound variables. And if you represent them as terms, well, you have the ability to perform hash counting and memorization. And that was not done by Le Charlier before. But this is essential to obtain decent performance. When I implemented it, hash counting and memorization, I obtained a 10x improvement. And this is not something surprising. If you read the papers about abstract interpretation for C, like the Astray papers, they have the same, they notice the same improvements when they use hash counting and memorization. Okay, so if we try to compare this to the work of Pessoa and Leroy, well, they also infer recursive types. But their technique is based on unification, whereas we instead use a fixed point iteration, so that's a different technique. They support arrow types. Okay, it's a sort of traditional type and effect system, so they have row variables to have polymorphism on effects for arrows. We do not have arrow types, but we are able to infer sets of closures, which means that when functions are really used as first-class citizens in a program, we might be more precise than Pessoa and Leroy. Considering integers, Leroy and Pessoa were able to express that, well, this value should be an integer that is either 1 or 3. Okay, so a finite number of possible integers, or any integer, or, well, some integer represented by some row variable row that will be instantiated later. Okay, but here this is quite limiting information. And we don't make a choice in our implementation about how to represent integers. We just provide a bunch of abstract domains, classic abstract domains to represent integers, and it's up to the user of the analyzer to make his choice. When we compare the control flow analysis, so traditionally, control flow analysis in the abstract domains, they try to avoid recursion at all costs because it's really difficult to deal with. Okay, I haven't told you, but especially the widening operator that introduces the mu construct. Well, it's difficult to get it right. Okay, so in all the previous work, they avoid this recursion, and instead they encode the recursion to express recursive sets of values using pointer indirections. But these pointers are abstract pointers in an abstract heap. Okay, so here it's basically the same value that I've showed you before. That is the set of continuations that are passed to the CPS factorial function. But here you notice that the recursion here goes through a pointer that is defined in an abstract heap. Okay, so and in modern papers about CFA, this is explained the following way. Well, it basically mimics the way a compiler works because it will allocate these functions in the heap. But in practice, it inhibits quite a lot of sharing between abstract values because what matters most is the names of these pointers. Okay, and this is also the main ingredient that makes these analyses converge to a fixed point. It's that the possible names of these pointers are in a finite number. And another thing that is not that great about the previous work about CFAs is that this abstract heap that is used to represent these indirections is global and used in a context insensitive way, and that hinders them from refining information when traversing a if-then-else branch, for instance, because to keep the analysis correct, well, you can't do that always. You basically have to perform a weak update instead of a strong update, and you lose a lot of information. So I told you that we define the analyzer using a dynamic fixed point solver. You might not know what this is. So, in a nutshell, it's a function that has this type. It takes a functional as argument and returns you a function that is supposed to be a post-fixed point of the argument. And it allows you to define quite easily and elegantly an analyzer, let's say here for the lambda calculus. So I apply the fixed operator to a functional that expects as a first argument analyze, which is the fixed point that we are expecting. And that takes then as argument two things, a pair of a term f and the environment, and that will return as output the abstract values. And basically, it looks like a standard interpreter almost. So in the variable case, I just look up in the environment. In the lambda case, I will just create a closure. Here it's an abstract closure, okay? And in the application case, well, I will analyze the two parts, T1 and T2, and then I will ask for the closures in V1. And for all these closures, I will, so a closure is a variable, a term, and an abstract environment. I will call the analyzer on this term on the environment that is extended with the value V2, which was obtained by analyzing T2. And once I have computed all these possible results, then I take the join of them. So obviously, it means that the cleverness of the analysis doesn't rely on this part. It's really easy. So what is really subtle is fix, the function fix that implements the iteration strategy, and of course the domain D. Okay, and well, so we implemented the analyzer using this style, and we're quite happy about it. So again, this is not a new idea at all. The same guys, Hentenrich and Le Charlier, used the same technique to analyze product programs. And then the same technique was again advertised by Daré and his co-authors on this beautiful paper, Abstracting Definitional Interpreters. So they advocate the fact that you should define your abstract interpreter in open recursion style. So it's exactly what I told you on the previous slide. And it's actually used for, I would say, real analyzers. There's an analyzer for C programs that detects data races that is called Goblint. And they are extremely happy about it, obviously. But if you have paid attention on this week on Tuesday, there was also work talking about this, the fixed point algorithms session. Okay, so it's an idea that is very much in the air these days. Few information about the state of the implementation. Okay, so on the top is the very beginning of the compilation pipeline of the OCaml compiler. What we take as input is not is an AST that is obtained very early in the compilation pipeline. It's the types AST, and essentially it's an AST that has many cases. It's large. And we desugar it to a form that is a bit more simpler and easier to manage in our analyzer. So what is nice about the AST is that the names of the variables are resolved. You have access to all the type information that you need. But what is not great is that you have some redundant parts. So you have many parts that actually perform some pattern matching. You have several constructs that perform exception management, and the order of evaluation is not yet made explicit. Okay, so we have a first phase of desugaring that essentially introduces exactly one construct for pattern matching and exactly one construct for exception handling. Here it's basically a construct that expects two continuations, the success continuation and the exception continuation. And when possible, we introduce let bindings just to make the order of evaluation explicit. And another thing that is very important for us is what I call pattern disambiguation. So basically here, you all know that in ML and OCaml, when you evaluate some pattern matching branches, you evaluate them in the order that was written. So when you know that some branch has failed, you get some more information. So what we do is that we make this information explicit. So here we know that on the second branch, well, this underscore cannot be sum of something. So this is what we call complements, and there are several papers that talk about this already. And yeah, so this information is also very important, not just for our analyzer, but for any analyzer. If you guys want to analyze the OCaml programs one day, well, you will have this information available if you start from the Salto AST. Maybe it's time to stop. So this is very much a work in progress. So far, we cannot handle the whole programming language, the whole OCaml programming language, but still our abstract interpreter is able to detect unquote exceptions fairly precisely. What I've showed you is a new abstract domain that represents inductively defined sets of values, and how you can use the dynamic fixed point solver to define your own analyzer. And I'd be happy to catch any questions that you may raise.
Thanks. So first, there are two parts of the question. The first part is how much precision do you lose when you have something you don't handle, a construct you haven't modeled yet, typically mutability. And second part, how do you intend to deal with mutability?
Okay, so the answer to the first part is really easy. So far, we fail. Okay. But of course, yes, we want to handle mutability. It's in the pipeline. Yes.
Thank you for the fun talk. So you've chosen to build this abstract interpretation on a quite early intermediate representation. You could imagine choosing a later Rowan. For example, we just saw a great talk about F lambda 2. And I was wondering about the trade-offs of those choices. I could imagine that a later representation might be simpler to work with because everything's already been destructured into blocks and you don't need as many different types in your abstract domain.
Yeah, so it's true that if you go later in the compilation phase, then your AST will be much smaller. That's true, but you also lose all or most of the type information. So far we don't use the type information, but we really want to, because sometimes the widening operator just makes the wrong choices, and in these cases it would be great that the output is refined by the compiler already knows. What else? It's also, I think, but please correct me, Pierre. I think it's also a bit easier to get more precise program locations so that you can more easily report to the programmer.
Any other questions?
So I'm wondering, how do you do the hash consing on the recursive types?
Well, these are just trees. Okay, so you have a node for the mu, and then the way we represent bound variables is using de Bruijn indices. So you have normal representation. So then you have just trees, and it's easy to hash count them.
And it obviously you implemented enough so you can try on larger programs. So what's your experience? What kind of large program you tried and how well it?
So far we have not tried on very large programs. Okay, the largest program we have tried with is maybe 200 lines. So we are very, very far from dealing with real-size code. And of course, there's this question of scalability. Will it scale to a large code base? So definitely not to Jane Street's code base. It's way too large. But I can't answer this question yet. My hope is that it will be okay. But I know that some trade-off will have to be made to degrade the precision in some cases, or maybe to find a more hybrid approach between whole program and fully modular function by function. Okay.
But scalability is, it just fails because out of memory or other things, so it just takes too long a time, and then you just give up. And what's the?
No, it's the time.
It's the time. Okay.
Yeah. Memory is okay-ish.
Yeah. Any other questions? Well, let's thank speaker again. This concludes our program for ML. Tomorrow will be also a CAML workshop, which is kind of related in some sense. Well, thank you for coming.
Too many questions. I don't know how to close this. Yeah.